Going to get started. Feel free to keep mingling and getting food anytime you want it, drinks, that's why they're back there. Everyone online, can you hear me okay? Guess I won't know unless you put it in chat. Okay, I got a thumbs up. All right, excellent. Thanks, Alex. All right, well, it's my pleasure to be here. Thank you all for coming. I'm really excited that we're all here. We're all together to celebrate all of the work that the students did this summer. It's been absolutely awesome and exciting to get to know all of them. Trinity, we're just starting. Good timing. So thank you all for coming. I want to start by giving all of the students a round of applause for all of the work they do, to congratulate them. I know you're probably all still nervous for one more day, but it will all be over in a few hours. I also want to thank everyone at the DBMI. I'm going to thank a lot of people today. At the graduation, I'll thank a lot more. But I want to thank the people at the DBMI who make the CoSBBI site, the Computer Science, Biology, and Biomedical Informatics site possible. Starting from the top with my department chair, Mike Bisich, who is very supportive of this program and supportive of me and my time so that I can do this program, to our training program director, Harry Hawkeiser, and all of our wonderful faculty, some of which are here today, who work with students and give of their time. All of the mentors in this program are volunteers. None of them is this a required part of their job. They're all giving their time. And they're doing it because it's exciting to work with you and because we all believe in the same mission, that it's important to train all of you because you are going to be the ones who revolutionize this world. And we want rooms around the country to look more like this room than they look now. So that's the goal of our program, and our faculty believe in that, and I'm blessed to have them as colleagues. So thanks to all of my colleagues, the trainees, faculty who are, and staff who are part of the DBMI, to all the wonderful people like Barb and Tony and Janine are outside helping you get here and get in, even our building manager who's opening up the space to us. So there's a lot of people who go into this that make it possible, and I just want to thank them before we start. Okay, but a point of order, the way we'll go, because I just want to jump in, I want to stay on time. We have a lot of talks today. How the talks will go is I'm going to ask the mentor to come up and to introduce the student who's about to present. There are itineraries in front of hopefully everyone, so you can see kind of as we're going along. When it's their time, come on up and talk. I'm going to try to handle the AV while you're talking. So don't be confused if I'm up here doing things on the laptop as well. We will be switching. We have a few students who are presenting remotely as well. So this is a hybrid event, but I'm going to try to control the AV. You introduce the student. The student was tasked to present for 8 to 10 minutes, and then we'll have a few minutes for questions. These questions can be about the science. It can be about how their summer was. It can be about what they want to do next. Feel free to ask them anything while they're up here. But that's how we're going to do it. But to try to get started on time, I want to begin by our first talk.
So hello, everybody. It's my pleasure to introduce Preetam. Preetam is going into his senior year at South Fayette High School. This is his second year at the Hillman Academy. Preetam has worked on several projects already. Just to name a few: multiple sclerosis knee brace, where he was involved in developing a knee brace to automatically stimulate the peroneal nerve to cause dorsiflexion in individuals suffering from drop foot associated with multiple sclerosis. He was also involved with developing a machine learning model for determining mammograms with breast cancer with high precision and accuracy. He's had a number of achievements. He has placed first in regionals for video game design, coding, webmaster, and he's placed fourth in nationals for introduction to information technology. So without further ado, Preetam will give us a presentation, Deep MT GAN, Artificially Intelligent Molecular Transformer and Generative adversarial network. And one other thing I should say is, actually, I'm introducing Preetam on behalf of Dr. Shaun Shia, who's really been his main mentor over at the School of Pharmacy. But it's been a privilege for us to have him. Preetam?
Thank you, Dr. McGuire, for the introduction and just for working with me all summer, even though I know where absolutely nothing in our building is, even now. Today, I'll be talking about deep empty GAN. I know it's a lot of words and it's 8 a.m., but don't be scared. I'll try to explain all of it. All right, so I wanted to start off today with the case study. I know it sounds fun, but we're all familiar with COVID, and it changed all of our lives. And in particular, it put a huge amount of stress on our healthcare systems. And in one way that COVID actually showed the bright spot in our healthcare system, or so we thought at the time, was the development of a drug called Paxlovid. It was developed by Pfizer starting in around 2019, 2020, when the pandemic started. And it went to clinical trials by the time we hit July of 2021, still within the pandemic, and even reached FDA approval earlier this year. And so this drug was kind of a wonder at the time, because it's almost unheard of for a drug to reach FDA approval within 3 years of actually being discovered and starting clinical trials. And this was really a testament to how we could respond to emergency situations, or was it? If we look a lot closer at the development of the drug as a total, we can see dating back to 2003 and another SARS outbreak, researchers actually identified and started studying Paxlovid all the way back 20 years ago. So even in one of our best moments as a healthcare system, it still took around 2 decades just to develop one drug, and it still came out by the time the pandemic was in its waning stages. And so obviously, drug development has a problem. It's insanely long, and it cannot respond quickly to emergency situations until we essentially get lucky and already have a chemical waiting for us that we could potentially use. And so how have we gone about trying to fasten that process in the past, present, and future? Starting with the past, we have high throughput screening. So basically what high throughput screening is, we have these chemical libraries of around 2 million compounds, and then a chemist or a biologist will go into a lab and they will test hundreds or thousands of these compounds all at one time to see if they're active in a certain part of the body. And so the problem with high throughput screening is extremely expensive just because of the amount of tests you have to run. You have to go to a wet lab with almost little information and basically make educated guesses from what you can tell from other compounds. And it has an extremely low hit rate of almost 0.01%. Oftentimes you can go and test thousands of compounds and not have a single drug candidate on the other side. And so currently, especially with the booming artificial intelligence industry in almost every different field, we started using computational screening to try and screen more drugs before we get to the lab. However, computational screening has another problem, in that sometimes it'll eliminate too many drugs or not enough. And it also cannot generate new molecules, so we still have to rely on chemists and biologists to go into the lab and formulate compounds that could potentially be active in a certain part of the body. It's still a very long process that is very iterative and takes a lot of time. And so that brings us to the future with generative AI. Now, we've all seen ChatGPT, and it shows huge promise in creating content without a human actually going in and training it. And so my hypothesis this summer was if we could use generative AI to do the same thing in biology. But generative AI has a secret. It displays a huge tendency to overfit, and it struggles to generate actually novel data, especially in a field like biology, where you can tell very clearly what already exists and what doesn't, unlike with text. And so if you look at this graph on the left-hand side, you'll see these green, pink, and blue curves. The blue curve is the training data, and it's molecules that we know actually exist. And the green and pink curves are curves from a machine learning algorithm that tried to generate new molecules. And so we can see that oftentimes the entirety of the blue curve is being missed out on, and that means we're not covering the entire chemical space that we possibly could. And if we look at this map on the right side, we can see again this huge amount of blue dots, and then a small cluster of colored dots in the very center, showing that we can only capture a little bit of the data using current AI algorithms. So what I wanted to test this summer was if artificial intelligence algorithms can generate drug candidates given information we already know and still produce higher yield rates than we currently have. And can we rely on such an approach to produce actually new molecules that are still chemically feasible? And so no model is better than the data it's trained on. So we decided to train on around 7,000 receptors for the dopamine 2 receptor and around 2,500 for cannabinoid 2 receptor, mostly because of data availability to us and how both of these receptors are relatively unstudied in terms of generative AI. And so the data we actually use and the way we represented these molecules is known as SMILES, Simplified Molecular Input Line Entry System. And that is basically a fancy way to say we took 3D molecules and represented them as strings in a way that's understandable in the biology community, almost like a biological language per se. So if we look at this top right orange box on the left-hand side, that's an example molecule, and that's what these strings look like. They're basically a string of different characters in English and then mathematical symbols, usually drawn from the periodic table. And so then if we look on the right side of that arrow, we can see a map of numbers. And basically how we made this readable to an actual machine is we took these strings and mapped them one-to-one from each letter to each number. So for example, in this string, an N would be equal to a 12, but this is an extremely lossy way to do it just because of the fact that you're losing out on all the structural information. So for example, if I have 6 carbons in a row, an actual biologist will be able to recognize them and see that's a carbon ring, but a computer would just see 6 carbons in a row and it would never think of more of that. And that's the main problem with this data. Another thing that we tried to do was we tried to capture a really broad chemical space. So if you look at these graphs on the bottom side of this slide, we can see that all these graphs are pretty evenly distributed and they cover a really large space. So QED is a measure of growth likeness, and we can see QEDs going from 0 all the way up to nearly 1, with 0 meaning that it's not really fit to actually be used, and 1 meaning it's basically the perfect candidate. And the reason why we included imperfect drugs that already exist is so that we could further increase the randomness and the novelty of the molecules we are actually generating. But how will we actually go about using this data? So we looked at ChatGPT and natural language processing just because of the way we were dealing with text and saw how we could apply it to biological tasks. So on the left-hand side, we have what's known as a transformer. This is what Google's BERT and other popular language algorithms are based off of. And it's basically an encoder-decoder network where the encoder will take in text or those tokenized versions of text, and they will attempt to represent it in a different space with just numbers that can potentially relate to one another. So that if I say the sentence, I have a car, it goes fast, we know that it refers to the car, but a computer doesn't. So what the transformer does is finds mathematical relationships within data automatically and autonomously so that it can also realize that it and the word car are related. I won't go into the details of how it does that because that's beyond the scope of the study. And so for the actual generation of molecules, because now we have more enhanced data, we use the GAN, or generative adversarial network, which basically has a generator and a discriminator, with the generator producing data that at first is random and over time becomes trained, and a discriminator that basically can tell whether data is real or fake. And so this was our general workflow. So if we start at the top here, we have those 2,700 SMILES that attach to one receptor in the human body that we started off with, and we tokenize them, which is that one-to-one mapping of letters to numbers. And then what we did with these tokenizations is we used them to train that transformer to learn how to represent them in a different chemical space that is more understandable to a machine. And so we took what they're called 2D embeddings, is what the output of this transformer is called. So we took these 2D embeddings, which are huge arrays of around size 32 different numbers, and we fed them into the GAN so that it could train itself to create 2D embeddings that are very similar to the one that it inputted. And so using those 2D embeddings that are now created randomly at first and then trained over time to model the original data, we can then decode that back up and we'll get in a theoretically novel SMILE string that matches the same language as the original but varies in the actual details. So this all sounds great in theory, but how does it actually work in practice? So with the transformer, we can see that it displays extreme potential for reducing vocabulary size, and it's very good at translating this original textual data to actual numerical representations that a model can use more accurately. So again, if we look at this orange box, we can see that same workflow of the SMILES to the tokenized version, and now we can see the 2D embedding on the right-hand side. And what's not displayed on here is that middle array is usually around a length of 510 because there's 510 different characters that can be in a SMILE string. But on the right-hand side, it's only 32 elements, which means that it's able to capture 510 data points and around 32 different numbers or 32 different ranges. And so this is extremely important for what are known as downstream tasks when you use another model on this data, because it helps new models capture the relationships more efficiently, and therefore they can work better and be more interpretable, especially to a biologist or a chemist. And it's also preserves structural information, like the example with the car, where it'll be able to relate to itself and learn over time how to actually produce SMILES that make sense while understanding why they make sense. And so these two graphs on the bottom just show the general performance of the model. And we can see as it's trained over time, the loss decreases, which means it gets much better at reconstructing its original data. And so how does the actual generation look in practice? So currently we're only running preliminary tests because the training of a GAN network is extremely complex and hard to do in around 8 weeks. And we're currently still tuning hyperparameters and seeing exactly how we can get the best possible results. But so far in preliminary tests, we can see that basically the computer is learning to speak around the same language that we're expecting it to. So on the right-hand side are actual SMILES compounds that we can actually formulate in a lab and can test to see if they attach to a certain part of the human body. And they work in practice. And then on the left-hand side, we can see example molecules that are being generated by a computer. And so the main trends in this data is there's a lot of carbon because it's the most common material. And so the computer oftentimes gets fooled by itself and ends up just producing long carbon strings. And on the other hand, it also produces extremely short strings that could be only 1 or 2 compounds that don't really help us in the actual world. But we can also see that even without a lot of fine tuning, there are certain molecules that reach a decent length and actually show extreme novel creations and different bonds than you would actually see in the training data, meaning that while we're able to capture some of that same language, we're still introducing randomness and new findings to the biological community that could end up helping us in drug development so that a chemist doesn't have to do this entire process in a lab over and over and over again. And so the conclusions we drew is that currently, generative AI is still flawed, but it shows good potential for actually being able to be used in the real world. And so if we continue training and testing the model with greater resources, fine-tune the hyperparameters to get better results, and further analyze these SMILES compounds both using computers and in a wet lab, we could further test the advocacy of using GAN models and different generative AI in the biological fields and see if they genuinely put up the results we expect them to in theory. So first off, I'd like to thank the audience for being here, especially so early in the morning. I know I didn't want to wake up. I'd like to thank Dr. Shia, who's not here today. He's in Boston for a conference, but he's helped me with a lot of this work and really just held my hand through the entire process. And thank you to Dr. McGuire for, especially in the beginning, showing me where everything is and just being a helping hand whenever I needed it. Thank you, Dr. Boone, for arranging all of this. Thank you, Stephen, who I don't think is in here today, for also arranging everything. Also, thank you to the NIH for the different grants to our laboratory and the University of Pittsburgh and the Hillman Academy. Thank you. Any questions? I love it when there's no questions.
I just have one with the, you said you made like essentially kind of like new structure for that, the model could represent the 3D things like without being glossy. I think I part of what I planned.
I don't think I explained that perfectly, but SMILES is basically, it's like in the biological community, it's like an established way to represent these molecules. So we didn't create that. It's just like a common way of representing them using text. But it loses out on a lot of like the structural information, because if you think of like an actual molecule when you see it, that's different than when you put it in the text, so you lose a lot of information.
Okay, is there like, I guess my question is that, is there like a structure, like, or like a way of modeling that maintains structure?
They're just like super computationally expensive. So like, just like go through one molecule, you'll need like an entire GPU for like 5 minutes. So I didn't really want to work with such complex data. Thank you. Any other questions? All right, good job, Preetam. Thank you very much.
Thank you. And I think what's exciting, you'll see for those of you who stay all day, the range of projects this year, because we have people from outside of the Hillman Academy, is kind of amazing. We'll have hardcore bioinformatics, biomedical informatics, then we'll have a clinical research study, we'll have public health interventions. We have all kinds of things today that you get to see.
Should I start?
Yeah, go ahead.
Okay, it's my pleasure. I'm Peggy Rosenzweig. I'm from the Pitt School of Nursing and have been working in the Hillman Summer Academy for many years. It's always such a pleasure. Our student this summer was Chimdi Isiguzo, who is a rising junior at SciTech, right down the street from the School of Nursing. And often, you know, when you do evaluations for students, you're asked if you what's the unique qualities about these students. And for Chimdi, I think this summer I have come to recognize that she's quiet and but is able to have information kind of one time, retain that, apply it in a really extraordinary fashion. And it has been such a pleasure to work with her. And we have think we're going to think big things for her in the future. Our team is interested in equity in cancer treatment. And what are some of the barriers to patients in achieving that? And I've always worked in breast cancer, but we expanded a little bit and had some funding from Genentech Corporation to look at advanced stage lung cancer. And those results and that exploration is what Chimdi's going to share with you.
Good morning, everyone. This summer, I had the opportunity to work with Dr. Peg and Dr. Ruth on stress and treatment tolerance among patients with late-stage non-small cell lung cancer, and it focused on a comparison between race and neighborhoods. So the roles of stress in cancer. Stress caused by adversity, depression, anxiety, and loneliness can weaken the immune system and potentially impact cancer growth. Inside the cancer cell is the tumor microenvironment, and there's a picture of that on the left. And stress may influence the TME through things like natural killer cells and interleukins through a stress response. So cancer disparities in survival, time to cancer progression, and treatment tolerance are affected by factors such as lifetime stress and exposure to racism, discrimination, and poverty, potentially impacting a patient's ability to endure life-prolonging cancer treatment. These social factors can play a significant role in determining cancer outcomes and treatment responses. So our hypothesis suggests that patients who have experienced lifetime stress due to poverty, discrimination, and racism may arrive at cancer care with elevated stress levels and could be less tolerant of the initial cancer treatment. So for this study, we broke up the aims into 3 parts. And the first aim is to describe baseline lifetime stress, physical symptoms, financial toxicity, allostatic load, and immune markers among patients with late-stage lung cancer, comparing by race and neighborhood deprivation. The second aim was to examine symptom distress during advanced lung cancer treatment at 3 months and comparing by race and neighborhood deprivation. And finally, the third aim was to compare dose modifications and disease progression according to the race and income of a patient. And we also broke up the methods into 3 parts. And the first part is the study design, which was a prospective repeated measures cohort design. And we had 3 time points, the baseline, the 3-month, and 6 months. And we recruited different patients from 3 sites in the UPMC cancer centers. And the next one is the data collection, which focused on statistical analysis and the description, comparison of means, and correlational analysis. And finally, the instruments. For baseline, we used valid and reliable measures of lifetime stress, discrimination, and symptoms. Allostatic load. Allostatic load is the wear and tear on the body, which accumulates as an individual is exposed to more stress. The immune markers, race, and the deprivation index, which was based on the zip codes. And for the 3 months marker, we used valid and reliable scales of patients' reported symptoms and treatment distress, chart reviews, the dose of cancer treatment modified or stopped early, and the interviews that we took from the patients. And then the results. So for this study, we had a total of 29 patients, 17 females and 12 males. Around 70% of the population was white and 30% of the population was Black, we had a mean age of 61.7, and the average area deprivation index was 68.3, and the baseline performance status, which is measured between 0 and 3, had an average of 0.61. So the first aim, like I said, describes baseline patient factors among patients with late-stage lung cancer, comparing by race and neighborhoods. Sorry. So there were, for lifetime stress, physical function, financial toxicity, anxiety, fatigue, pain, and allostatic load, there are no statistical differences between Black and white patients, except for the experiences of discrimination, both lifetime and daily. There are differences for higher neighborhood deprivation in physical functions and allostatic load. And our second aim was to examine symptom distress during advanced lung cancer treatment at 3 months, comparing by race and neighborhood deprivation. There were significant differences for Black patients with financial distress at 3 months. There were significant differences for patients for higher deprivation for physical function, and pain, and fatigue. I forgot to mention that the numbers highlighted in orange are all significant data points. And finally, for the third aim, which was to describe treatment modifications and disease progression according to race and income. Overall, there were 10 patients who had doses modified in the first 3 months and 8 patients who had disease progression. And overall, Black patients had fewer dose modifications compared to white patients. And there were no differences in treatment modifications and disease progression according to neighborhoods. Through the content and analysis, we described that the following themes. We described that the challenges that patients faced adjusting to the illness, the uncertainty about living with a dire prognosis, their life plans and family issues, and their difficulties with their current setting with care and confidence in care. And it was not always the case for some patients due to past experiences, and there were no appreciable differences according to race and income. In conclusion, although there are differences according to race and income in baseline and 3-month measures, there are no racial or income differences in the outcomes of dose modifications and disease progression. There are differences in symptom profiles that demand attention. Just as treatment can be tailored to individual, the symptom and distress profiles can be predicted according to demographics and social determinants of health. And finally, this provides guidance for proactive symptom and distress reducing strategies. Thank you. And I'd like to thank Dr. Peg and Dr. Ruth for guiding me through this study. Also, Dr. Boone for all the lectures that we had over here. And finally, Hillman for accepting me to the program.
Any questions? Chimdi, in your qualitative analysis, when you were looking at all of the charts, which are all of the interviews, that's a lot of work.
Yeah.
Can you tell me, like, was there anything that was surprising to you that you read from the interviews?
Actually, yes. So when I was reading the interviews, I was looking out for people who didn't trust the healthcare system. And surprisingly, all of the patients trusted the healthcare system. They all said good things about the Hillman Cancer Center. They had positive reviews and all that. So that was one thing that was interesting, or like that spoke to me.
That's interesting. I wonder if.
Yeah, David, I don't know what is, but every interview we've ever done at the Hillman Cancer Center, would just say, this is a magical place. You know, I've had terrible experiences in healthcare before, but this doesn't happen here. So it is very specific because we don't hear.
That's interesting. I wonder if that's like a bias of people agreeing to do the interviews.
Maybe, yeah, that they're more inclined to praise, but it is surprising.
That's very surprising.
Sorry to interrupt.
No, that's really surprising. Any other questions? Great job. Chairman, is that 23? Yeah, I hope this.
Good morning. My name is Greg Cooper. I'm a faculty member in the Department of Biomedical Informatics here. And it's been a real pleasure for me to work and serve as a mentor to Jeremiah Satcho this summer, who's a rising senior at North Allegheny Senior High School. Also serving as his mentor is Mr. Kevin Bowie, who's here. Who's a senior software engineer in the Department of Biomedical Informatics here as well, and also Dr. Ye, who's back here, who was instrumental in preparing much of the data used in this project, which was a significant task. In summary, Jeremiah did an excellent job as an intern, and it really was great to work with him. His project required him to learn about two different, quite different and challenging fields of research. One is biosurveillance of disease outbreaks, and the other quite different field is causal discovery from observational data. And I was really impressed with how Jeremiah learned these fields sufficiently well in a very short amount of time in order to be able to do the research at their intersection that he'll be talking about. He also showed a high degree of commitment to the project and worked very hard. And as the project evolved and some of our plans necessarily changed, he did a really fine job of adapting to the needed changes, which, as we all know in research, is an important quality. In doing so, he was quite calm and collected under pressure, which is another nice quality. In addition, Jeremiah worked well with Mr. Bowie on the computational aspects of the project and with Dr. Ye on the data aspects. In about just 6 weeks, he applied the computational methods he'll discuss, as well as analyzed and reported the results. So I'd like to now turn the floor over to him for his talk on that has to do with the topic of detecting changes in the clinical presentation of influenza using causal machine learning. Jeremiah.
Thank you. Thank you for the introduction. Good morning, everyone. My name's, as Dr. Cooper mentioned, Jeremiah Satcho. My mentors were Dr. Greg Cooper and Mr. Kevin Bowie, and we were also aided by Dr. Ye. And the title of my presentation is Detecting Changes in Influenza Clinical Presentation Using Causal Machine Learning. So as Dr. Cooper mentioned, we used an approach that falls under biosurveillance. And so the definition of biosurveillance is the field of study concerned with the monitoring and detecting of diseases in a population, particularly infectious diseases. So our biosurveillance approach causally characterizes the clinical presentation of known outbreaks of diseases to gain insight about these diseases. So through our study, we also had to apply causal discovery, which is an area of machine learning that is concerned with the learning of causal relationships from data under assumptions, including learning solely from observational data such as medical records. And the medical records that we got were from hospitals such as Shadyside and Children's Hospital and Presbyterian Hospital. So we're looking at influenza. And so influenza is a contagious viral respiratory tract infection that can exhibit changes from year to year. And by analyzing these changes, we can have further insight into these diseases. And so we're applying causal discovery to influenza so that we could determine which clinical features were caused by influenza and determine the changes from year to year. So our hypothesis was that there will be substantial similarities and differences in the findings caused by influenza from year to year. So the methods we used were processing patient data, running computational tests, and analyzing causal results. first part, processing patient data. So we started by assembling the data set, and this included data from the years 2013 to 2015, and we broke it up into two cohorts. So 2013 and 2014 had 384 patients that were known to have influenza, and that was matched with 384 patients that were influenza negative. And in the cohort of 2014 and 2015, that had 709 known influenza patients, which were matched with 709 patients that were influenza negative. So then we wrote a program to replace the code names of the different features and to facilitate the understanding of our analysis. So for example, if I put up on the board, if the code was like C5563DJD98, nobody would know what that is. So we basically just replaced that with fever, which everyone can understand what that is. So when we're making all these causal models and everything, we can actually know what we're looking at. And so we use Java to program this. So we ran computational tests, and we used Tetrad, which my mentor Kevin Bowie actually worked on a lot. And so he was actually expert when aiding me in this. And so Tetrad is a software program that estimates causal relationships from observational data sets using a variety of algorithms. And so as you can see on the left, we have a screenshot of the page that we use. And so up here is year one. So this would be 2013 to 2014. And so we get the data from there and put it there. And then in the knowledge, we would be able to filter out like demographics that wouldn't actually have any causal relationships, like age wouldn't really be causing influenza, or influenza wouldn't cause AIDS. So we could just eliminate those. And then we ran a search, and in the search, we could decide which algorithm we were going to choose. And so we applied the PC stable algorithm to test for dependence in the data set among the elements. And then we graphed causal models, which are just graphs that have the elements and edges that determine whether they're causing or caused by influenza. So then we analyzed the causal results. So to do this, we coded a program through Java to organize the findings by year and reliability according to the bootstrap method. And so this method just applies multiple randomized tests with replacement of the elements to basically determine the frequency that these would be seen and the reliability of our results. So then we created a chart from the periods 2013, 2014, and another chart for 2014, 2015. And these two charts displayed the findings that were caused by influenza. And then by looking at these findings, we're able to, by looking at these charts, we're able to compare the findings and determine similarities and differences. And so we were able to derive a chart that had only unique features for year two, which was 2014 and 2015. And these unique results would show new features that popped up that were caused by influenza. So we would be able to see changes. So these are the first two charts, and on the left is the chart from 2013 and 2014. And as you can see on the top, 0.5 is the first threshold, and it goes to 1. And so a threshold of 0.5 would just mean that it had a 50% frequency. And we started from 0.5 just to block out any noise, because if it's below 0.5, then there's probably little chance that it would actually be caused by influenza. And so as you can see, fever, which is highlighted in yellow, it had a 100% frequency in our test. And for example, you'd be able to compare these two charts to see which ones would be similar. And then we'd also be able to see difference from looking at these charts. So red throat was shown to be caused by influenza above 90% of the time in the year 2014 and 2015, but it was not shown at all in 2013, 2014. So this shows that there was a new feature. And this translates to our next slide, which shows just the clinical findings that were unique to year two. And so, as I mentioned before in the blue, red throat was shown. And then we could also see back pain being a new feature that was shown above 90% of the time. So we can conclude that the presence of common and unique features over consecutive years supports our hypothesis that there would be substantial similarities and differences in the findings that were caused by influenza from year to year. And so this was useful because it supports the efficacy of our process in being able to compare different years consecutively. And so we could apply this to other diseases, but for future research, we would most likely use a larger number of years. Because since we only use 2013 to 2014, that's a small number, and having like maybe 100 years would make the information more reliable. And then we'd also enlist biological experts to help solidify our findings. I'd like to acknowledge Dr. Greg Cooper. He's been very helpful. Although this is the first time I've actually met him in person. We've been working together through Zoom almost every day. He's been available all the time for any questions I have. And yeah, he's very busy, but I never felt that like I was gonna fall behind or anything. And I'd also like to thank Mr. Kevin Bowie, because he's just a computer science expert, and he'd be explaining all these topics to me, and it felt like I was in like a college course trying to learn all this stuff. But yeah, he did a really good job. And then I'd also like to thank Dr. Ye, who, as Dr. Cooper mentioned, she gave us prepared data that we were able to use and process, and without her, we wouldn't be able to have this project. I'd also like to thank National Cancer Institute for funding us, or funding me in the YES program. And then Dr. Boone as well, because he's been very helpful to me with a bunch of random things, knowing where to go. And I also like to thank Stephen Jones. I don't have him on the side, sorry, but yeah, he's also been a big help to me. And then the UPMC and University of Pittsburgh. Thank you.
Any questions? We've already asked you guys a million questions, but I'll keep asking. So Jibraan, do you think that from the differences you're seeing from year to year, could it possibly be a biological difference because the strains are slightly different from year to year?
Yeah, it could be. That's why we need to include like a biological expert, or go from a biological standpoint and analyzing the data further to further validify our results and also get further insight.
Yeah, that'd be interesting. It'd be interesting if you have data from where there's like H1N1 for outbreak or some big known outbreak of influenza versus another year.
Yeah.
That's cool. Right. Any other questions? Good job.
Thank you.
Hi everyone, my name's Eddie Perez, and I'm a doctoral student here at the Department of Biomedical Informatics. This summer, I had the pleasure of working with Alex Schafer. He's going to become a senior now at Alderdice High School, and he did a lot of work for this project. Here with you, Alex.
All right, hello everyone. Welcome to the Heathrow Airport in London. Thank you, Eddie, for the introduction. My name is Alex Schafer, and I will be presenting about a project aiming to create a pipeline to explain a GRED model trained on clinical data with missing values. So imagine you don't know whether you should go to Gen Ed or not. And here I come, a predictive AI telling you there's a very high chance that you should. Now you have no idea what you need, so you just end up scouring your fridge and pantry. This is effectively what some clinicians have to deal with when getting predictions from predictive AI. That's where explainable AI comes in. Instead of not knowing what you need from Gen Ed, I could tell you that you're almost out of milk and coffee. Now let's look at the real thing. An AI model is predicting whether a dire outcome will occur in a patient. The model gives a high prediction value, specifically 0.977. With this information, a clinician does not have much direction other than that a dire outcome most likely occur within a patient. Like milk and coffee, the most important factors in prediction are albumin and lactate. With this information, a clinician can cater a treatment to the patient just like how you can effectively go to Django. Explainable AI can also show if the model is trustworthy. For example, if the explanation said the AI model found Swedish Oreos in your house and said that was a good reason to go to the store, you'd probably question it and not go to the store. This is similar to how a clinician can view predictive AI. For example, if a patient has a completely normal temperature of 98.6, and that's the reason an AI is making a prediction of a dire outcome, the clinician will most likely question the prediction as a whole. One main complication that differs from this example is that clinical data is time series, not static. The image shown is a small portion of a single patient in the clinical data set. Notice that there are lots of missing values in the clinical data. Clinical data like this leads to challenges when finding ways to explain models trained on it. The first challenge is the limited availability of time-aware explainable AI methods because most research on explainers has focused on static data. Although there has been some more recent focus on time-aware explainers, most of them are model-specific. We found 3 model-agnostic time-aware XAI methods. The next challenge is the limited availability of explainable AI methods that can handle missing data. Of 3 explainers we found, only TimeChat could address both challenges, as well as provide both local and global explanations. Shown is a flowchart representing the steps on a typical model-agnostic explainer working with a predictive model. Because of the nature of clinical data, we need to impute missing values, but we don't know why the data is missing. This brings up challenges when finding an effective way of imputing data. A GRUD is a predictive model made for time series data that also imputes missing data using a decay function. Like the model, the explainer also needs to be able to handle the missing data. With a few changes to TimeChat code, you were able to explain the GRUD model using both local and global explanations. Local explanations explain just one prediction, while global explanations show the most influencing factors for the entire model. The data used to train the model is open source data from PhysioNet. The data contains 12,000 cardiology ICU patients with 37 variables and 48 time steps. The prediction target for the data set is patient mortality in the ICU. A GRUD is an RNN built on a GRU architecture. Shown is a diagram of how the GRUD model works. The initial data is sent into the GRU architecture, which weighs the time steps based on distance from the outcome. After that, the GRUD model calculates the decay factor for the imputation of the missing data, then creates a function that utilizes the decay factor to impute the missing data with real numbers. The model then trains on this data and loops it back around to the GRU until there's no significant improvement. Once the loop is over, the GRUD is trained. After the training is done, TimeChat uses the same training data and creates new samples by changing every variable at every time step. TimeChat feeds these new samples to the GRUD model to create predictions. TimeChat also requires a baseline calculation, which is the average patient of the data set. With this baseline, GRUD creates a baseline prediction that TimeChat can base its importance values from. With these predictions, TimeChat can estimate importance values for each variable over each time step. In order to be compatible with TimeChat, we had to make some modifications to the GRUD. Because GRUD was created in a way that does not allow for predictions on new data, the first modification was the addition of a prediction method for single samples, because TimeChat requires the GRUD to generate new predictions from altered data one at a time. The next change was to substitute missing values with 0 when calling the predict method, because the model will try to find the average of the features, causing a missing value as a prediction. This would not allow TimeChat to perform the predictions needed to find importance values.
This is further supported with this heat map of RNA-seq, which is also 1993 cells. Whenever we reach.
We also had to alter TimeChat code to handle missing values. The change that we made was to the baseline function. In the original timeshot baseline function, timeshot would attempt to take a median part of the data, but because of the missing values, there was a low chance that the output would be a real number. To bypass this, we use NumPy's NaN median method, which would take the medians of the data while completely ignoring the missing values. This allowed for timeshot baseline prediction to find the importance values. A global explanation is the explanation of the entire data set of predictions. In this case, we can see that the most important features are usually Glasgow Coma scale and respiratory rate. We can also see that the only events that had a noticeable impact were the final 13 time steps. With this information, we can alter the data so that only the last 13 time steps were available to the model. By doing this, not only are the calculations much quicker, but the plot is clearer for users. Changing the number of time steps in the data also changes model performance. At first glance, you can see improvement in ROC-AUC, PR-AUC, and F1 score. But when you look deeper, you can see that although the false positives decreased, the false negatives increased, creating a trade-off as a result of eliminating time steps. A local explanation is an explanation that shows feature and event importance for a single sample. These line plots show the sum of feature importance values over time. In the sample with the highest direct outcome probability, we can see that the last 5 time steps were the most important to the prediction. In the sample with the lowest direct outcome probability, we can see that the last 6 time steps were most important to the prediction. These plots show the most important features to the prediction. In the highest probability sample, we can see that albumin and lactate are most important to the prediction. In the lowest probability sample, we see that white blood cell count and troponin T are most important to the prediction. With altered timeshot and GRUD code, we were able to create a pipeline that presents both global and local explanations. An evaluation of the global explanation allows for improvement of the model. The local plot displayed valuable information for single predictions in a way that is comprehensible. Related future work should focus on the limitations of the GRUD and timeshot. The first is because GRUD was not made to predict on each sample. Defining an effective way of looking value implications, specifically when trying to predict on a single sample, is important. Future work can also assess timeshot accuracy and imputation methods are implemented. Another limitation is the slight timeshot accuracy error that was found when explaining of the lowest probability sample. Future work can assess when negative values are involved in the calculations. Finally, this pipeline should be tested on other clinical data sets to ensure accuracy in both GRUD model and timeshot. Thank you to Stephen Jones, David Boone, and all of Hillman Cancer Center Academy for doing this. A huge thank you to Eddie, being my mentor and being awesome. And our collaborators, Santa Fe, Gary, and Chris for that. Any questions?
We have a question online. Go ahead, Chad.
Hi, thanks, Alex. Can you say a little bit about how clinicians could actually make use of these results in helping them with patients?
Well, when they get a prediction, say high positive prediction that shows a dire outcome could occur in a patient, alongside these explanations like bad albumin amount or of some sort, they can use that knowledge rather than just general knowledge of, yeah, this is going to happen, to cater more of a specialized treatment to the patient.
Any other questions? All right, Alex, I'm glad it's all worked out and you were able to present from the airport. How did it feel to present in the middle of an airport?
It's interesting. There's a lot going on.
Yeah, I'm sure. Well, thanks, Alex. Enjoy your trip and we'll see you soon.
Thank you. See ya.
Bye. All right. So I'd see, Spandon or Janish, are you here or online? Didn't see you. If not, I'll introduce Jibraan. So it's good to see Jibraan. Jibraan is a second-year student in the Hillman Academy, but last year he worked in the cancer biology side doing wet lab because he was very interested in wet lab work. But we were able to convince him this year to take a flip over to the dark side of computational research. So here he is. He's worked remotely this entire summer, one of a couple of students that you'll meet today. So Jibraan, thanks for being here, and go ahead and take it away.
Awesome. Thank you for the introduction. Again, my name is Jibraan, and I just graduated from Canton High School, and I'll be attending Drexel University in the fall. I was mentored by Yamnesh Agarwal, a PhD student, and Dr. Spandan Maiti and Dr. Maiti's lab. And the name of my project is the use of digital screening to further improve intervention methods for aneurysms of the ascending aorta. All right, so just to start with some background, the reason that we focused my project on the aorta specifically was to improve the prevention strategies for type A aortic dissection. We're doing this research to learn more about when to intervene for treatment. Type A aortic dissection is a highly lethal event and has a mortality rate of 1 to 2% per hour for the first 48 hours. The current size for dissecting the aorta has to be above 5.5 centimeters. But again, by the time for dissection, the intervention can be too invasive or stressful for the patient. Therefore, better prediction metrics are critical for better intervention methods. Large retrospective series and data from the International Registry of Acute Aortic Dissection have showed us that over 60% of patients with TAAD have aortic calibers that are less than 5.5 centimeters, yet most patients with aortic diameters less than 5.5 centimeters never dissect. So again, this shows us that we need better intervention. So basically throughout the project, I was able to, since I'm completely remote, this was something new to me, but I used a software called AnyDesk to sign into the lab's computers so I could access all of the necessary softwares and programs. And I did this to construct a series of geometries to see basically how the aneurysm acts at different points over the cardiac cycle. All right, so again, we're focusing on type A aortic dissection. In the picture to the right, it shows you the difference. Type A is specifically in the part of the aorta that comes directly out of the heart, the ascending aorta. And it is a very serious condition because it is very dangerous. It basically happens when there is a tear in the inner layer of the body's main artery. It is the largest blood vessel in the body, so a tear in your aorta is obviously very bad, and it can lead to cardiac tamponade, pleural rupture, or even a stroke. Here's another diagram of that. If the blood goes outside the aortic wall, it is often fatal. A lot of patients die due to internal bleeding. Here are the software programs that I have learned and used throughout this project. Again, AnyDesk has allowed me to do everything from my house. Next, I use 3D Slicer. 3D Slicer is where I used 3 different views of CT scans to reconstruct the heart. And then Mesh Mixer was used to smooth and enhance the model. So here on the pictures, you can see this is all in the 3D Slicer. So the first part of using the 3D Slicer was to apply the threshold. So basically the program or the software will go in and it'll highlight all the lighter colored tissue. And unfortunately, this includes the spinal cord and certain arteries that I don't need. So there's a a little bit of a tedious process going through and manually reconstructing the heart. So over my time during this project, I reconstructed a few different patients' hearts. And yeah, it was really cool to be able to do something like that. And then here are screenshots that I took from the mesh mixer. This is that same heart in the last slide after I trimmed it and smoothed it out. And you can see the aneurysm in the ascending aorta. You can see it better on the picture on the right, the big bulge. So again, this is cool to see the patient's heart on my computer screen at home. So just to make it easier to follow, the method of me doing this really shortened is for me to log into the lab computers using AnyDesk, and then I would upload the DICOM data to the 3D slicer. DICOM stands for Digital Imaging and Communications in Medicine. So basically, there was different patient data, and all the patient data had 3 separate scans for the thoracic region. First, I would apply the threshold in the 3D slicer, and then I would manually track the heart CT scan in the 3D slicer. So again, this involves removing any non-cardiac tissue, filling in any areas that the software missed, and erasing any areas that the software selected. Next, I would transfer the file to the mesh mixer to smooth out any discrepancies. Unfortunately, I wasn't able to complete the project as much as I was hoping to, but luckily, being remote, I can continue to work on this project in the summer. The next step for me in this project would be to use the multiple 3D CT scans that I made to create a 4D scan that would show us the aneurysm sort of in real time as the heart beats. It kind of looks like a GIF. And by doing this, we can put the aortic aneurysm under different conditions using certain softwares. And for example, if we put more stress on the aortic aneurysm, it could tell us a better time to intervene. So yeah, in the future, those will definitely be my next steps. I would like to give a special thanks to Dr. Spandan Maiti and Yamesh Agrawal for mentoring me and teaching me about this new side of research that was really confusing me at first. I'm not the most technological person. I would also like to thank David Boone for everything this year and last year. It was really cool to be a part of the CoSBBI site this year. And again, I would like to thank Stephen Jones and the UPMC research program in its entirety for giving me the opportunity to learn something like this 2 years in a row.
Any questions? So Jibraan, do you think you're going to go back into wet labs, or you're going to keep doing computational research?
I'm definitely more of a hands-on person, so I think I'm going to go back to the wet lab. But it was very interesting to do this project still.
Very cool. Any other questions for Jibraan? No, good job. All right. So next, Daniel is online. He wants to introduce Samantha.
Hello, everyone. Hello, it is my pleasure to work with Samantha again. This is the second summer we've worked together. We worked on med design and working in the lab here at University of Pittsburgh. So there have 2 just recent undergraduates, postdocs working with her this summer. She's been fabulous. It's been a very busy summer, but Now we're finally done. Congratulations. So she's ready to start UConn in the fall. Is that right? Yes, that's right. Congratulations. We are so proud of you. And I'll turn it over to Samantha now. Hello, everyone. My name is Samantha. This is my sign name, American Sign Language. So yes, I just graduated from the Student Center I apologize. So I'm going to be a freshman this year at UConn in the fall. The Learning Center for the Deaf was my high school, to clarify. So now I'll begin my presentation. So my research was on the topic of physicochemical and ADMET pharmacokinetic properties of potential inhibitors of the PLK1 protein in cancer therapy. So first I'll introduce PLK1 in cancer. PLK1 is polyleucokinase. That's a crucial protein. It supports and promotes cell division and mitosis in eukaryotic or animal cells. So drug compounds that would be inhibiting the polobox domain, that's a domain where PLK1 is found in the cell. So they may be able to stop the cancer cell growth and division. So these images here, these graphics show how PLK1 works in cancer cells. So we would like to find a drug that would inhibit that division by targeting PLK1. So I'll go ahead and explain the goals of my research. So we received 46 compounds, 46 molecules that were identified from a total of 6 million compounds in a database. So those were identified through that high throughput screening by our collaborators. So they gave us 46 compounds that seemed that they may be promising PLK1 inhibitors in a polybox domain. So for my study and my research, I'm showing physicochemical properties, including solubility, lipophilicity, absorption, distribution, metabolism, excretion, and toxicity or ADMET properties of the different molecules to improve data analysis precision and representation. So this graphic here shows one well-known drug called thymoquinone and how it binds to PLK1, binding again to inhibit PLK1 from becoming active. So all of this research was done computationally. The goal is to have that analysis, the possible analysis of those ADMET properties through the computation framework, and then take that to the wet lab. Now the wet lab is really costly, really expensive. So we're trying to reduce the time by analyzing each of these parameters ahead of time for each of these compounds. The only issue with this, we have a great deal of data, massive amount of data. So what we had to do was narrow that down to get more specific data in order to identify the best drugs to target PLK1. So what I'll be showing you is our methods for doing that. The first step of our process was to create 3D structures of our 46 molecules. Secondly, we converted those molecules into the coding language called SMILES, S-M-I-L-E-S, to make it possible for our software to use that in our screening process. Thirdly, we used that formatting. We went to ADMET Lab 2.0 and Swiss ADME. Those were our two softwares that we used to screen all 46 compounds. Lastly, when we collected that data, we were able to analyze it, narrow it down, and remove less quality compounds, and then we could create that analysis in graphical presentation. So now, this is one of the representation of one of our properties, right? So here I show that representation for the physicochemical results. This image is called a radar chart. So we were able to identify the 24 compounds out of the 46 that had more ideal properties for the physicochemical aspect of this. So this involved solubility, as well as structural features and lipophilicity degrees. So you can see each of those lines, colored lines, different colors represents the molecules, one of the molecules that we were analyzing. So this blue line here, for example, is molecule number 33. And you can trace that around. So that was how we use that chart. So this is all the different data values for each of these properties. One thing that I noticed in my research was that each of the compounds showed promising effects for physicochemical properties, had this type of scaffold, that ring structure. So, and it had 2 nitrogen bonds in it. Next, I'm going to focus on the medicinal and chemical properties here. So these are different types of drug rules. So you can see with these drug rules, the first one, for example, Lipinski rule of 5. So compounds 12, 19, 29, 34, 35, 42, 43, all of those were the drugs that failed those rules and those tests. So there are many different compounds that fail these different rules and tests. So, you know, if it fails a rule, it may not be the best for medicinal chemistry. I'm not sure it may not be good for these. So, you know, we have the GSK rule. That's a parameter. So you see those lines here, those fail because they don't have good metrics for this. Chelating potential, that relates to how a medication interacts with the metals in the body. Of course, that can be important as well. Now, these other here, bioavailability, synthetic accessibility. So we're thinking about how our body interacts with these drugs with all these different goals. Next, I will discuss absorption and distribution. That's AD in ADMET, that acronym. So here we see this boiled egg diagram here, this depiction. We have a chart here. You see the yellow circle represents the blood-brain barrier. That larger white oval represents human intestinal absorption, HIA. Blue shows PGP, and that's polyglycoprotein. The red shows that it does not have affinity, it's not a substrate. And the blue shows that it is. So next, here we have all 46. The next slide will show the best compounds using this chart and this analysis. So these are more promising properties regarding absorption and distribution. So we want PGP to not be a substrate, and we want it to be within that human intestinal absorption range, which is good. That blood-brain barrier, that yellow bit, is optional. Yeah, our research showed in the literature that the blood-brain barrier is not absolutely necessary for this therapy. So 26 out of 46 of our compounds passed this or showed promise in this. Now, we're going to focus on our results related to metabolism at the end and at that. So this shows all 46 of our compounds related to their probability of having affinity with that cytochrome P450 enzyme. So whether those are inhibitors or substrates. So you can see number 1, for example. So that blue section there on the bottom of number 1, it's very small. That represents cytochrome P450 IA2 inhibition. The probability of that is almost 0, it's very small. However, above that, that red section, that larger part, shows CYP1A2 substrate, and that has a higher probability. So you can see that goes up to 1. However, the next graphic, I'll show you more narrowed down version of those more best potential candidates using this property of metabolism. So we've removed those over 4. So as you can see, this narrows it down quite a bit. This has 17 molecules in it. So those drugs that have a higher affinity with CYP450 will be quicker for the body to metabolize, or will be harder for the body to metabolize. So we want that to have a lower probability. So now we're going to talk about E, that stands for excretion. So this shows different half-life potentials and different clearances for excretion from the body. So what we want in this case for these drugs would be having higher half-lives and medium clearance. So as you can see, for example, number 10. This is good potential because it has a high half-life probability and medium clearance. So we want that to be between 5 and 15, and it's here 9, 10, that's good. Next image will show us the best candidates using this property. So this is narrowed down, right? You can see it's only those with high half-lives and those with medium clearances. Lastly, T, this is toxicity. So this image shows for each compound the number of toxicophores and endpoints. So we have 4, 3, 2, 1, and 0. So the drugs with 4, that's quite high, that's quite toxic, so we removed those, and we actually narrowed it down because we thought it would be best for these to be between 1 and 2. So we want 1 to 2. That's the best level of toxicophores for these. Unfortunately, all cancer drugs will be toxic because they have to interact with those cancer cells. So these are the results for the medications, what we wanted for our medications. So now, finally, I'll go ahead and summarize all of this research that we've done and all of the images that we've looked at. So these are all the different properties that we analyzed, and the lists show what were the most promising candidates for each property. So as far as my results, one, that those that passed all 6, including ADMET properties, there was only one, that was number 18. That seems like the best candidate for this. In order to pass 5 properties, if we remove toxicity from them, that included numbers 2, 5, 18, 22, 23, 26, and 27. So those were the most promising relating to those ADMET characteristics. So now, of course, I want to thank my mentors. I had 4 mentors: Dr. Montserrat Lawal, Dr. Tuba Kuchikov, Adiba Wale-Bogachiran, Dr. Lundberg, the Gallaudet Design Lab, and of course, the interpreters. So I'd like to thank you for working with me for all 7 weeks of the program. On Zoom, of course, Joshua and Marcus. Thank you.
Good job. Any questions?
Go ahead. Were you surprised to find that certain drugs were able to pass the blood-brain barrier? That's kind of an interesting finding.
Yeah, let me show you that blood-brain barrier. I mean, that's to explain to that, that's not really important for cancer therapy, so it's not required, but yes.
Thank you.
And Samantha, is there plans for the lab to now validate, I think it was number 18, but whatever your best candidate was?
Yes, 18 as well as those other 5 that were good. So that's a good question. So those molecules are going to be tested again. They're going to be researched in the wet lab at Gallaudet University in their research lab. So in their medicinal lab. So, you know, we have that computerized data, that computational data will continue to be analyzed first. And then hopefully, yes, it'll match, the computerized data will match the potential with the wet lab in order to test all of these drugs. And hopefully that will be able to, that design process will be able to be applied to other drug development in the future for other cancer and disease drugs as well.
Excellent. All right.
Thank you.
All right, can we give one more round of applause for everyone who presented in the first session? You did a great job. And now we're going to take a break until 9:40. So we'll start right back on time at 9:40. Restrooms are right on the other side of this wall, so you can walk out this door and around. There's still some water, bagels, fruit, things in the back. Help yourself. Take a break.
The part.
It's like.
Yeah, what's up?
I shared with you my presentation on PowerPoint because whenever I put it into like the OneDrive as a PDF, I don't think I can see my speaker notes.
That's, yes, you're exactly right. You have to
So-
do PowerPoint to see speaker notes.
I'll just share.
Do you want to, I think I have you, you're in session 2, right?
3.
You're in session 3. We can take a look.
I was just making sure because I don't have my thing memorized, so I just would like to see.
So here are your slides. We can take a look.
Oh, perfect.
These are the right ones, right?
Yeah,
You're good to go then.
perfect. Thank you so much.
Yeah. What's it? That's not so bad.
So now it's back at one.
Yeah. Whose are these? These are your new, our two. Okay, and I'll let Rich know that we gave him Janine. That's perfect. I'll give him the Janine who's around. Sweet. Cool. Okay, great. So I'll see you at 2
See you at
o'clock.
graduation, yeah.
But we'll be there for 1. Oh, yeah. That's perfect. Yeah.
And that'll be in the same location.
It'll be, yeah, she might be, or they might be out in front, but it's like,
We'll see,
you'll
just
find it.
Oakland.
Will it be best, should I bring this camera, or you wanna work out close?
I would bring it just in case. I have mine.
Okay. Yeah, because we're gonna be then one in
Right.
person and one.
Yeah, right.
So, okay, I'll bring that camera and then we'll figure out.
Yeah, I have a camera, I don't know.
Yeah, and if you, well, you're going over one, we'll have lunch here at 12:30. There's Chipotle here.
Okay. Now you're speaking my language.
I'm just letting you know.
Chipotle as well.
Yeah, it'll be right out here in the hallway.
Sweet, thank you.
Thanks so much. I understand that.
A little bit.
A lot more. And I put that there in case like. So I have to agree that when mean by what you're saying. So give us some idea. Yeah. Because we could always be like, could always
That was her. Words that mean nothing. That's the hard part. Especially with the.
Oh, actually, before I forget, I saw you put your badge in there. Can I have your badge?
Yeah. Yeah, that's fine. I like, we're not even. Her presentations. Almost as well, because we can't just rely on figuring out how long to go. Also why there's two. We have previous talks on the different programs. Where the roles, so yeah, I was so glad I saw you putting that away, even though literally, so. Yeah. So it's. And I can get whatever. So then I also need to be able to see some. It takes. Great. They have representation. In the day, they are working. They do all their. Okay. Part of the regular, and we have. We're doing a lot of work here. Yeah. I've been home for a while years now. But I'm also. John, you have your my year beforehand, I always older and first. Now I don't. I'm also now, all I want right now is. Hillman stuff, you know. With someone else. Okay, that's why I don't run into it. I'm more.
Oh, okay. Now this is, the summer. Yeah. One project. Yeah.
Like this, yeah. Usually when we sign love, make a better. I'm not. Possibly. Oh, no, my. Yeah. So, yeah, and then we work on it.
Yeah.
Like our number.
Yeah.
All of the ASL parts, and then like for me, I.
So, yeah.
Like that one, look at.
Yeah.
Just. Over like, those words makes them like. Because if you're so generous. For things, and I give them, it might be a different, like, all right, I get it.
Yeah.
So you really trying to look at it. Yeah, and then. You're.
Yeah.
Just the point.
No, of course.
And then of course.
I mean, trying to get it.
I try to talk, like, the questions like, who's going to see it? So, you know, it's like, also there's like, it's not great.
At that time. My agent told me, you know. I put down,
They're the ones who.
I was paying for a house. My agent came and told me that. Hey, you know, I'm gonna- It's great.
Where you don't want to turn to the next stage.
Right, like, you know.
I would be like, no.
I do need your badge. Just the badge to get individual. Oh, yeah. Give you my temporary. You ready? Sign on.
Yeah.
You'll be. Sign that. That doesn't work. Whatever we can do.
Just sign here.
Yeah, just sign there.
Okay.
The thing is that I did enough money for a good chunk of down. Yeah, so I have a lot of cash down here, but now I'm fine now. Because I held it.
Thanks, Doctor.
Triple.
Yeah, maybe it's good.
No, double, triple, yeah. Oh, yeah.
Imagine that.
Everyone's.
Good, good. Yeah, no, it's all good. I'm running off here, so it's not wavy. Yeah. It's all good.
I brought that block in that I was telling you about, to raise
Okay.
that up. I
Yeah.
don't know if you wanna try it and see how it is, or just leave it alone for right now.
It doesn't really matter, I think, at this point. Okay, we're good. All right, thanks.
I don't know now. Yeah, I look at the price. Yeah. Yeah, my friend. And I look at this. They did the 180. When it was yeah, $184. But the cost of the client will be it's 181. Yeah, and
If anybody.
Yeah, they have a seat. I'm tired.
Yeah. So I just over. Yeah. Actually. And then jumped down. It's good. Because these are right now. Good luck. That starts in yeah. Like each day. Oh, yeah.
It was, so basically I was working with
We'll start. I'm still trying to get she like try to do it online, but she's not good. So if so, we'll start out with. Just to give you a heads up. Oh, yeah. Well, I was like, all right, I had to take it out. Whoa, that's another story. I hate that.
That's all. Oh, yeah.
I could have done it in like, this is already stream.
I haven't done third.
I would not publish it. Yeah, I would not do that. All right, so apparently. Well, thanks, Betty, and like. I still. No, I was like. Yeah. So I'm. Oh, I think you can tell us about. Yeah, basically.
I feel like why it is. But like up the class.
So our next speaker just messaged me and said she's very sick and isn't coming. So we're gonna wait about another 3 minutes and then we're gonna start with Jose. But just so we're not too far in front of schedule, make sure all of our mentors get here to introduce everyone. We're gonna wait about another 3 minutes and then I'll bring us all back. So keep getting food, drinks, talking, and we'll start again soon. I saw you walking by. I saw you.
Yeah. They have like this crazy. It was like even for it was like a quarter and a half. He tried it like 20 times. I know. Yeah. I saw the calling came in after that. But I always saw what you did. Thank you. Over here. Is Gabriel or something you're using?
Not impossible.
What about,
Sick.
we've been.
If you want to take the talk.
I think you were telling me that, yeah, that's angry.
I heard that like.
Yeah, no. Yeah, volleyball.
I'm getting conditioned now. I'll hit you.
Yeah, it's even better to like, I don't get around like the whole. Yeah.
All right, I think we're gonna get started on our, I don't think that, we're gonna get started on the second session. And again, for those of you following along at home, we're gonna skip over one presenter and we're gonna start with Jose. But before we do, again, I want to thank everyone for being here. For anyone who may have just came in, thanked everyone at the beginning, but thanks to all the students for all the hard work that you put into the summer, and all the mentors, all my colleagues, all the graduate students, postdocs, trainees, faculty who have helped with the students. Thank you so much for working with these students. But why don't we get started now with Billy?
Hi, everyone. My name is William Reynolds. I'm a graduate student in the Department of Biomedical Informatics here. I had the pleasure to work with Jose this summer. He's going to be going into a senior year at Chimdi Academy. It's always a challenge with the students, we're asking them to do a lot in 8 weeks, really understand a problem and then try to solve that problem. And Jose did a really great job this summer of looking into and studying the congenital heart disease and neurodevelopmental world, and then using computational tools to try and go and solve those problems. And he did a really great job. So, thank you, Jose. So without anything further, Jose is going to give a great presentation about congenital heart disease and brain development. Thank you.
All right, guys. Hey, I'm Jose Maldonado. I go to school at Chimdi Academy, and my project was on exploring the effects of congenital heart disease on brain MRI registration. Thank you to my mentors, Raphael Seskin, William Reynolds, and Joy Roy. So, brain magnetic resonance imaging. What is it? Magnetic resonance imaging, or MRIs, work by utilizing the magnetic properties of hydrogen to generate precise images of the body. And thankfully, we have a lot of hydrogen in our body. We have hydrogen concentrated mainly in water and fat, which our brain has a lot of. And that's why we use brain MRIs to study neurodevelopment. Brain MRIs can show us abnormalities and irregularities in head size and brain structures. And they're pretty safe. It's a painless procedure, and there's no radiation produced in the scanning process. An imaging technique called image registration is also used to study neurodevelopment. Image registration is a process of aligning one image onto another. It's very useful to compare these two images, and the diagram on the right shows how it works. So essentially, we have two images. The top image, we want to look more like the bottom image. So the registration algorithm has what's called a cost function, which evaluates how similar these two images are. Right now on the left, these images are not too similar. So the algorithm will say, okay, let's run this through an alignment algorithm until the cost function says, okay, these images are similar enough. And we get to a point on the right where the images are in the same space, same orientations, and etc. This is a toy example. And this is a more, this is a more realistic example pulled from our study. This is a fetal scan on the top and a neonatal scan on the bottom. Neonatal means just after birth. And this is a scan of the brain. So to compare these two images, we wanted this image to look more like this one. And as you can see, the orientation, the size has changed to make the fetal scan look more like the neonatal scan. So congenital heart disease is a cardiac disorder. It's a malformation of the heart in the terms of shape, size, or structure. And although it's not a neurological disease, neurocognitive deficits are not uncommon in CHD patients. Neurocognitive deficits, such as in executive functions like planning and impulse control, or learning disorders, can be found in many CHD patients. However, the causes of these neurological impairments that are associated with CHD are pretty complex, but scientists like to pinpoint them to genetic and environmental factors. With this study, we want to better understand the difference between CHD and neurotypical brain development in a measurable way. Okay, so within our study, we had 69 total subjects. 2 of our subjects were excluded because their neonatal scan was taken after a year of birth, and that was just out of the age range. So within our 67 subjects, we had 19 CHDs and 48 controls. Each subject had 2 time points, 1 scan of the fetal brain and 1 scan of the brain after birth. And we hypothesized that differences in registration between CHD and control can be indicative of abnormal brain growth. So first, we scanned the brain of our babies at a fetal time point and at a time point after birth. We recorded the age at the time of the scan and the time duration between the scans. And then we pre-processed the scans by skull stripping each scan to remove non-brain tissue. You can see the skull strip process take place here. Essentially, the skull, the facial structures, and the neck are all removed to just have the brain in the image. This is better for comparison analysis and improved registration performance. Then we registered the images. We registered the fetal image onto the neonatal image. So we wanted the fetal image to look more like the neonatal image. And we recorded the correlation ratio. The correlation ratio is a cost function that we discussed earlier, which evaluates how similar these two images were. We use this correlation ratio as a similarity metric, and we analyze how the time duration between the scans and the age at the time of the scan correlated with it. And we also examine the population distribution differences. Okay, and here are our results. So firstly, on the x-axis, we have the fetal gestational age. On the y-axis, we have the similarity score. The blue group is a control, and the CHD group is a red. Within the controls, we found a positive correlation between the fetal age and the similarity score. And this makes sense. Fetal brain development is really quick, especially compared to the afterbirth. And with more time spent in the fetus, the more brain development that's going to occur, and thus, the less similar the two images will be. We did not find a statistically significant correlation within CHDs in this graph. And then for our next graph, on the x-axis, we have the time duration between the scans, and on the y-axis, we have the similarity score. Again, within the controls, we found a negative correlation between the time duration and the similarity score. And this also makes sense. This is intuitive because the more time spent between the two scans, the more neurodevelopment that will occur, and thus the less similar the images will be. Again, we did not find a statistically significant correlation within CHGs. However, we found a positive correlation opposite, which is pretty interesting. But we think the reason why we couldn't find a statistically significant correlation for our CHGs is because of the high variability in neurodevelopmental outcomes within CHGs. What I mean by this is many CHG patients will go throughout their lives without experiencing any neurocognitive deficits, and thus any neurodevelopmental abnormalities. And this high variability, this high variance in these outcomes could probably be the reason why we couldn't find a concrete solid evidence correlation. As you can see, the red dots are scattered all over the plots, and you can't really make a solid correlation using the CHD data. So in the future, we hope to study this issue with more data, more subjects, and we hope to control for social determinants of health, like financial status. We also hope to control for scan time. CHD mothers are more willing to get scanned because of clinical reasons. So we could probably homogenize the scan times by getting a later scan time for the CHDs. We also want to expand the study on older age ranges and investigate neurodevelopment and neurodevelopmental outcomes into adolescents and adult populations. And that's my study. Many thanks to Dr. Ishak Panigrahi, Dr. Raphael Seskin, William Reynolds, and Joy Roy, Dr. David Boone, Stephen Jones, the Department of Biomedical Informatics and the Hillman Cancer Center, the Robert Wood Johnson Foundation, the Doris Duke Foundation, and the National Institutes of Health. Thank you, guys. Any questions?
Forgive me if I missed it and wasn't your presentation, but what was the similarity score comparing?
So the similarity score was comparing the two images, the fetal scan and the neonatal scan. And we're talking the scan of the brain while I was in the fetus and the scan of the brain after birth. And it was comparing the similarity between the two to maybe see any neurodevelopment as a proxy for neurodevelopment in between. Does that make sense?
So at every time frame, you were comparing it to the fetal development, or do you compare between intervals?
No, we only had two scans.
Oh, you just had two scans?
Yeah.
Okay.
The fetal scan and then the scan after birth, and we compared the two using the cost function of the registration algorithm. Any other questions?
Seeing a low similarity, no correlation, low similarity score.
Yeah.
Across the board, like seeing no effect on time. Wouldn't that mean that
there is something going on?
So a lower similarity score would mean the brains are more similar, right? And excuse me. A lower similarity score would mean the brains are more different. And that means there's probably been some structural development in the brain between the two scans. A higher score would mean there'd be less growth in the brain and hence the increased similarity. So yeah.
Another question? Yeah, that's it. Thank you.
Hi, good morning, everyone. So my name is Xinhua Lu. I'm professor at Department of Biomedical Informatics. And this summer, I really have a pleasure to work with Dylan Zhang, and who is a rising senior from Hillman Academy. Yeah. So Dylan, I'm really impressed by what Dylan has been done in this summer, few weeks. And he has been interested in the biomedicine, I think it's for a while. Last summer, he spent the whole summer in Brown University and do some basic research, which is on the drug sensitivity related to. And this week, this 8 weeks, and we work together to try to mine the spatial, more advanced, most recent cutting edge technology data as a spatial sequencing on studying how the ovarian cancer originated and how the different stage. And I'm impressed by his independence. All the code is written by him and everything works. And also Dylan and I share some common interest in photography, right? So that's about it. Without further ado, Dylan.
That's my fault.
Okay, hi, I'm Dylan, and in my project, I investigated the transcriptomic changes in early stage ovarian cancer using spatial omic data. Ovarian cancer is a cancer that is difficult to detect. It has many variants, and many of those variants have a low survival rate. And a better understanding of the disease and its mechanisms is needed. The variant that I will be talking about today is serous tubal intraepithelial carcinoma, or STIC. STIC is a precursor lesion to HGSC, or a high-grade serous carcinoma. And in the pictures you'll see here is normal progression from normal epithelial cells all the way up to HGSC. So first you have your normal epithelial cells. Those are the little kind of square shaped cells. And eventually those have progressed to a P53 mutation. And the cells with the P53 mutation will eventually progress up to STIC, and eventually HGSC, and it'll metastasize and move to different parts of the body. STIC and HGSC don't just affect the epithelial cells, they also affect the stromal cells, so the diamond-shaped cells down here. Yeah. Digital spatial profiling is a spatial transcriptomic methodology that studies tissue samples for RNA and protein expression. And it also gives spatial information, so the spatial part of spatial transcriptomics. And it gives the cell's position in relation to neighbors and non-cellular structures. The DSP data is useful in determining phenotype, cell function, and cell signaling. Enrichment analysis is a method that takes a list of overrepresented genes and compares it to an existing database. It then outputs a list of likely biological processes that are significantly altered. So on the right, you'll see a really quick diagram of enrichment analysis. You have your list of genes. Sorry, that should be genes, not proteins. And you compare it to a database. In our case, we use the gene ontology database, and it'll spit out a list of processes which are likely to have a significant change in between two groups. So our objectives were to find out which genes were differentially expressed between stick and normal epithelial cells, and also what impact stick has on its surrounding environment. The data set that we used was a DSP data set collected from 54 regions and 95 samples. Tissue tested included both stick and surrounding normal epithelial and stromal cells. To analyze this data set, we compared stick and normal epithelial and stromal cells. We tested for a significant change in expression using a t-test, conducted a gene ontology enrichment analysis, and analyzed the functions of the differentially expressed genes. These are two volcano plots. So the one on the left compares stick and normal epithelial cells, and the one on the right compares stick and normal stromal cells and gene expression in those cells. So a volcano plot basically just shows significance and difference in between two groups. So the further away from zero, the more difference was expressed, and then the higher up it is, the more significant the result. All of the results above the blue dotted lines were statistically significant. And so all of the genes highlighted in red were also significant. And I just highlighted a few special genes which contribute to some of the biological processes that I'll go over in a second. So after running an enrichment analysis, we found a list of biological processes that were significantly altered in epithelial cells. That included mesenchyme development, regulation of the WNT signaling pathway, regulation of apoptosis, and positive regulation of DNA transcription. And stromal cells that included the positive regulation of TGF, beta-1 production, the tyrosine kinase receptor signaling pathway, and extracellular matrix constituent secretion. So from that list of processes, we can take away a few takeaways. Epithelial cells lose their characteristics and gain mesenchymal characteristics, and that helps with movement through the bloodstream and lymphatic system, helping with metastasis. The extracellular matrix is also altered by stick. That impacts tumor growth, invasion, and metastasis. And TGF beta-1 upregulation also encourages the epithelial mesenchymal transition and has an immunosuppressive effect. Overall, the tumor microenvironment was changed, so the surrounding environment was changed. Epithelial mesenchymal transition was upregulated in epithelial cells. Metastatic potential was increased, and cell signaling was also increased. And I'd like to thank Dr. Liu, the Hillman Academy, and Dr. Rinda Soon for the data set.
Any questions?
So you highlighted a few genes that you said were kind of important or kind of novel. Do you think that you could maybe use those genes as a way to target this cancer, or is it something that you could give clinicians information about?
Yeah, certainly. Some of the genes highlighted, like I said, they are involved in the mesenchymal transition and also regulation of apoptosis. So perhaps if you inhibit those genes, then there will be some sort of effective cancer treatment then.
Any other questions? Right, good work.
Thank you.
Right, so it is my pleasure to introduce our next speaker, Abril, who had the misfortune of working with me the last couple of weeks. But it's been a lot of fun to get to know Abril over these last couple of weeks. She's a rising senior at Shadyside Academy, incredibly intelligent scholar like everyone else in this room, and does amazing things. I hear she's a great musician, which I would love to hear at some point in time. But she came to me only a couple of weeks ago. So what you're seeing is something that was condensed within a couple of weeks. So not over the full 7 or 8 weeks. And when she came, I really treated it almost like a hackathon. I said, here's some data that I'm very familiar with and we can have access to right now. Here's some techniques that I know how to do. Come up with a question and learn how to code in R, and let's do it. And she's done a great job and came up with, I think, a really interesting, important question. And so I'll turn it over to her to tell you about it.
Thank you, Dr. Brew. Yeah, so this summer I worked on differential gene expression analysis on tumors of Black and white women with triple negative breast cancer. So what is breast cancer? It's when there is an abnormal, uncontrolled growth of breast cells that form tumors. In the US, there is 264,000 women that are affected every year, and 42,000 die. And as you can see on the left, it is actually the top cancer by the number of new cancer cases for women in the US from the years 2016 to 2020. Breast cancer has 3 molecular subtypes. The first one is hormone receptor positive. So when the breast cancer has estrogen or progesterone receptors, the breast cancer becomes ER positive or PR positive. And here you can see in this pie chart, it is the most common in the dark pink. There are good targeted therapies for this molecular subtype, so that leads to good outcomes for these women. Some treatment options include, a treatment option is tamoxifen. This next one also has good targeted therapies, but not as good outcomes. HER2 positive, it's so when the HER2 protein, which helps regulate cell growth, and there's an overexpression of HER2, then the cancer cells multiply fast. The last one is the most aggressive subtype of the 3, triple negative breast cancer. When the breast cancer is negative for ER, PR, and HER2. Some treatment options include surgery, radiation, and chemotherapy, but unfortunately, there are no great therapies yet. Also, it is known that triple negative breast cancer affects Black women the most. And that's one of the reasons why I decided to focus on triple negative breast cancer this summer. So Black women have a higher frequency of triple negative breast cancer and the top death rate. So here you can see the frequency of TNBC for a European American woman and how it's so different from African American women and women with African ancestry. They have a higher frequency. And then because triple negative breast cancer is the most aggressive, this could explain why in general for breast cancer, Black women have the highest death rate. Some factors that could contribute to health disparities for Black women include socioeconomic factors, high prevalence of obesity, but the one I'll be focusing on is genetic risk factors, right? And so this all inspired my research question. Is there a difference in gene expression between the tumors of white and Black women with triple negative breast cancer? So the results of this question could help us understand biological differences based on race, with the hopes of identifying new clinical targets, and then design better therapies and understand why certain therapies don't work right now for triple negative breast cancer. I worked with 3 data sets. These were all from the Cancer Genome Atlas project. The first one, the TCGA outcome data, it had overall survival for 1,236 breast cancer patients. And then the second data set was clinical data, which had demographic and subtype data for 1,257 breast cancer patients. For all of these data sets, since they had data for breast cancer patients, first I had to determine the triple negative breast cancer status and filter out just have the triple negative patients. And then for the second data set, I merged it with race and tumor stage data. And after that, I was able to create a Kaplan-Meier curve using the outcome data and the clinical data. And then the third data set was transcript expression data, which I used along with the second data set to run DSeq for 55 Black patient tumors and 98 white patient tumors. So the first result, the Kaplan-Meier curve for overall survival, showed a trend for poorer overall survival for Black TNBC patients. So here on the y-axis, you can see the survival probability. It starts at 1, and then on the x-axis, the time in days for overall survival. I started with, down here is the number at risk. I started with 50 Black women and 87 white women. The blue line shows the white patients and the red line shows the Black patients. So as the lines become more separated, the survival probability becomes more different for the woman. So for example, here at 5 years, the survival probability for a white woman is around 90%, while for a Black woman, it's around 65%. And then I ran a chi-square test to determine if there was an enrichment of tumor stage based on race. The results showed that tumors for Black women were enriched for higher tumor stage. So then this led me to regress the tumor stage in the differential expression analysis I ran later. Then I made this PCA plot, but there were no really specific clusters. So gene expression alone could not explain all the differences because the clustering was weak by race, which is the red versus blue, and then even weaker by tumor stage, which is the circle versus the square. And then I made a heat map, but gene expression patterns were shown by this heat map. The Black patients, which is the green line, there seemed to be like a cluster right here, and then these had mostly yellow dots for these. So there was a pattern shown there. And then finally, this volcano plot showed several significantly differentially expressed genes between the Black and white tumors. So all these names are for genes that were significantly differentially expressed. And at the end, 512 genes were upregulated and 661 genes were downregulated. So some future research could include pathway analyses that could be performed on the differentially expressed genes. And then these could provide insight into the biological differences based on race with the hopes of identifying new clinical targets. We could also look at the genetic and epigenetic differences within triple negative breast cancer by race. So thank you everyone for listening. I'd like to thank my mentor, Dr. Boone, for his incredible mentorship this summer, the UPMC Hillman Cancer Center Academy, and the Doris Duke Foundation.
Any questions?
Why did you choose to look at the individual? I think you already mentioned how African and Hispanic women are more prone genetically, but is there any way?
Yeah, mostly because triple negative breast cancer affects Black women the most, but then I also chose to look at Black women and white women just because they had the most data. Like women like Hispanic women or like Native American women, there wasn't a lot of data for them. Yeah.
Okay, was there a reason for the different amounts of particular races of people? Like there are 98 white women and 55 Black women?
Yeah, so like for example here.
Yeah.
Yeah, so they just started, this data set just started with those amount of women that went into the clinic and like reported their stuff.
All right, thank you.
Yeah.
And I think to follow up, those are the ones of the 1,200, there were only about 200 that were triple negative. And then there was about 160 that had race associated with it, and gene expression, right? That was it all together. Yeah, it's good work. All right, next up is Trinity.
Hello, can you hear me?
Yes, go ahead, Jenny.
Hi, so my name's Jennifer Fry. I am a representative from the Division of Adolescent and Young Adult Medicine, and I'm just here to introduce Trinity. I want to say in the short time that I've worked with her that she has been a great addition to our lab, and I'm very excited to hear her presentation today.
Good morning, everyone. Before I get started, I wanted to mention I will be speaking about suicide. I know it's a sensitive topic, so if anyone's uncomfortable, I would suggest leave. Everyone good? Hi, my name is Trinidy Manison. I'm a senior at University Preparatory Malynn. This is my first year in the Hillman Academy, and I'm honored to present to you guys what the numbers say: depression, anxiety, and suicide within adolescents. My mentor was also Dr. Arora-Jain. So my study examines the statistics surrounding mental health in kids and implements possible solutions for adolescents struggling with mental illness, such as depression, anxiety, with the main focus on suicide. Depression and suicide are increasing in the US. In 2020, suicide was the second leading cause of death ages 10 to 14, which was national. Which in a third leading cause for suicide death was ages 15 to 24, according to the CDC. The year also in 2020 was a 28% increase within depressive symptoms, which grew from 193 million people to 246 million people as well. There was also a 25% increase with anxiety, which also grew from 298 million people to 374 million people worldwide. In Pennsylvania, teen suicide is 8.2 per 100,000 deaths, which makes it 36th in the nation for suicide. I have a graph right here, as you can see. At the bottom of the graph, you see ages 10 to 14. My graph ranges from 2009 to 2019. You can see that it increases, but if you look up to that green one, you can see that there also is a huge spike in ages 15 to 24, as I just mentioned, what was the third leading cause of death with adolescents in 2020. Now I want to talk about my problem. According to the UCLA Health, nearly 20% of suicidal teens report their suicidal thoughts. In an article released in 2023, from the National Council of Mental Health Wellbeing, 76% of Americans see mental health just as important as physical health. That's why there shouldn't be any lack of resources nor mental health resources as well. Another problem we have in America is affordable resources. If you compare the rich and the poor, rich people can afford resources when poor people can't. It can either lack from them having no insurance or them having bad insurance as well. Now that I've talked about that, I want to talk about my goal. My goal is to be a representative for peers to use their voice for such serious matters. Not me just being a Black 17-year-old female, but just being a teenager as well. I want to be a representation for teenagers to speak up about such serious issues. I also want to provide adolescents with resources I received from my lab. I worked with Dr. Arora-Jain. So what I'm presenting to you guys is a public health intervention to improve mental health and well-being for all adolescents, and also to increase mental health awareness. Now let's talk about my solution, which is SOFA, Supporting Our Valued Adolescents. SOFA is a website used by adolescents for free access to mental health resources. As you can see, I've inserted a picture here of our website. I clicked on the tab Crisis Support, and you can see that there is an abundance of things on here. I just want to point out two important things that are underserved representatives in Pennsylvania and worldwide as well, is LGBTQ+ resources, there's BIPOC resources, meaning Black and people of color, there's regular SOFA resources, and most importantly, there's crisis support resources, which is a very important thing. SOVA's website also provides user accounts where you can look and find many resources that you like, meaning that you're able to create an account and actually be a user on the website, but you are anonymous for your safety and other safety, which is important. And we thought it would be a great target audience because most teens use social media. So we thought it would be cool if they can create an account and actually use it like it's a social platform. And now we have SOVA can be used as a relatable experience where you're able to actually talk to others and talk to them if you're going through anything suicidal, depression, or anxiety. So you're able to actually talk to them like it's a regular platform, for example, like Instagram or something. Here's how I took action. We distributed SOVA resources across the Allegheny County. I gave 3 or more presentations to rooms of 40+ students, and I used clinic tips to have better presentations. So with that being said, I actually had a great opportunity to present in front of the Hillman Academy, which I'm presenting to you guys on behalf of to most of the people who are in this room, which is a pretty good experience. When I say using clinic tips to have better presentation, I was able to shadow Dr. Radovic in the clinic this year, which was an amazing experience because she deals with adolescents and most of them you have struggled with anxiety, depression, or suicidal thoughts. So I'm able to take what I've learned from her and present it to you guys today. I want to talk about the distribution. So I talked about sleep, stress management, and communication. It was a really cool experience. As you guys can see, I like SpongeBob. I made the sleep presentation and it was really cool because it was actually me making a presentation that was surrounded about mental health. I took 4 articles that was from the SOVA website and I made it into a presentation, and I also presented that to the Hillman Academy as well. Stress management and how it can affect your mental health and why it's important to keep it to a minimum. As you can see, that slide is in Spanish because SOVA got a great opportunity to present to the kids that were at the Latino community. So that was definitely a great experience. I didn't participate in it because I didn't know how to speak Spanish, but my coworkers did, and it was really cool. And then we have communication, and my coworker did that one, and it was really cool. I also presented to kids that were in Boys and Girls Clubs, like I said, the Latino community, and I also had an opportunity to present to Hillman this year, so that was fun. Now I want to talk about SOVA's end goal, and it provides youth with more than one option to receive support regarding mental health. Meaning I wanted to make sure that there were more resources for children, especially adolescents, especially like teenagers more so. The website can be used from ages 11 to 26 because those people are considered adolescents. But we wanted to make sure it was more so it's affordable because it's a free website, but they also have more support regarding mental health. My takeaway was definitely my impact. It's great to speak to kids who are the same age as me, that talk like me, that sound like me, that act like me, kids who kind of like are me. So it's definitely cool when you're able to present like such serious topics and kids tell you like, oh, that was really cool. I definitely listened to what you're saying. When I presented at Hillman and we went to the next keynote speaker the week after that, some girl told me that she puts her phone down for the first hour of the day because that's what I presented about when I presented at Hillman. So that was definitely a good takeaway. And it just boosts your confidence in that you're actually making an impact. Another takeaway I had was that no one's speaking about the issue, teens or adults. So no one's speaking about the prevention of suicide or how to have better resources for depression and anxiety. Nothing can get done about it. Also, we need more representation from adults and children as well. I want to acknowledge Dr. Anna Radovic for helping me with my presentation. I had a great experience. I want to thank Gabriel. I want to also thank the Hillman Academy for accepting me into their program. I had an amazing experience here. Thank you so much, Dr. Boone. And I want to thank the Doris Duke Foundation. Is there any questions? No. Yes.
Do you think that the spike in suicides amongst kids is more due to environmental, like where they live, or do you think it's like from like in school, like when people go to school, people bully and stuff like that? Like, you think this spike is more environmental or like more like something like a setting like this?
I honestly think it's both. I also think social media plays a big part in the increase in suicide. I mentioned in 2020 there was an increase with anxiety symptoms and depression symptoms, which also spiked from COVID. So
right. I was just about to ask,
yes.
do you think it came more because of the pandemic?
Yes. Any more questions?
Did you find some correlation between when someone is committing suicide with the family about someone else in danger for that situation?
No, it was more so general, if that makes more sense. So like how I mentioned in this slide. Give me 1 second. So in this slide, you can see I mentioned a picture of our website, and I don't know if you guys can see it, but there's like all types of different like resources there, but they're more so like underserved communities. So not more so family wise, but that's definitely a good question. But I was thinking more so like it was like a general like analysis more so, and worldwide. But I also mentioned Pennsylvania because I'm from Pennsylvania, and I wanted to show that we're actually like higher up when it comes to suicide. Any more questions? And seen somebody else raise their hand.
Actually, this is a great, yes, you had LGBTQ and BIPOC resources, and then also you mentioned talk to the Hispanic population. How important is it for relating your content to your specific group that you're going to be talking to and getting the resources?
That's a good question. It can be. So for when I present, it's different because you're speaking to, when I present to Shady Side Boys and Girls Club, I'm speaking to predominantly Black African-American teenagers, and also when I do it downtown. So it's definitely different when I'm presenting, but more so like when I'm speaking to Hillman, I have to be more so general because there are like hundreds of like races. So like in the room with me, like 80 kids on Zoom, in person, 40 kids in person, 40 kids on Zoom. So it's like I definitely have to switch it up when I'm presenting, but it's not too hard because I'm able to relate to mostly everyone. So yeah. Any more questions? Okay, thank you guys.
All right, so I just got an email from Adam's mentor saying that he is on his way, but is running late. So I will introduce you now, and when he comes, he can say all the wonderful things that he wants to say about you. So it's been a pleasure to have Adam Ferris, who's a rising senior at Fox Chapel, with us this summer. I was really excited when I read his application because I noticed he seemed to be really passionate about computer science and also about teaching it. So he started a program to teach technology to seniors. He helps to teach coding to middle school students. So I was really excited to have him. And not surprisingly, he was a great participant here. He was able to, again, you saw the wide variety of projects that are here, but Adam always had some really insightful questions that he asked in, I think, really polite ways to every student here. So it's been an absolute pleasure to have Adam around. And when Dr. Lee hopefully gets here on the bus, he can talk about you after your talk, but I'll leave it to you.
So much. All right, so I know we've talked a lot about what everyone's doing this summer, but I'd like to talk to you about something else, which is fall, but not the kind you're thinking of, not autumn. A big issue in our senior population is these high-risk falls in one's own home. You fall, especially as you get older, bones get more brittle, etc. You can suffer some pretty grievous injuries and even death from these falls. So, for example, according to the CDC, 36 million people each year in the US fall in their own home, leading to 32,000 deaths and billions in medical costs. So we have systems to try to reduce the effects of this by increasing response time. We have these wearable sensors, the Apple Watch actually has one built in, not sponsored, but and then we also have these ambient vision sensors, which is a fancy name for a camera or a series of cameras in one's house. And we focused on that second kind right here, because we feel there is an inefficiency in how people process this data. So we process video feed currently using these complex neural networks that can be very difficult to make. They're very accurate if you can make them work, but it takes a very long time to create a varied and effective data set, etc. And then the dense neuron, just essentially the big multiple layers of neurons, things like that, can just create a very inefficient model at computation, like when you're computing things, take a lot of resources. And then finally, just neural networks in general, so you can kind of see from the second image too, it's a little vague of like, what do you see? What do you think each neuron does there, right? It's hard to tell the inner workings of a neural network. I believe Alex Schafer earlier actually talked about this too. He had to create a whole model to explain an existing neural network because it's a little bit vague. So what we wanted to go for was a non-neural algorithm because we felt this would be, it would save a lot of time by avoiding this training process. It would be a lot more direct and thus efficient. You don't need to have a series of neurons interacting. And then finally, it's just a lot clearer how it works, which makes later improvements, changes, etc., much more easy and flexible. Of course, the downside of this is you have to find a way to define to a computer how to identify someone falling down. So that can be difficult to do. And also it can require some optimization, refinement. It's just a long process we aim to do. You can get yourself a pretty efficient program. So I'm essentially, the way I'm going to be explaining this, a little bit vague. I'm going to be explaining the processes we used, and it'll sound a little weird, but by the end of it, you'll see it'll all come together. So first up, we wanted to process to find motion in our video. So right here, you can see between these two, pretend these are much more than 5 pixel by 5 pixel images. You can see there's only one thing that changes, and it's these squares right here. So imagine if this is the new image, it moved from here to here. So with that, in that example, this, whenever you subtract these two images, each of these, each of these squares their values are subtracted from themselves. So that just subtracts to 0 in the end image, that top left pixel. And you do this for each and every pixel. So anywhere that something stayed the same, it just goes to 0. So you only detect the motion right here. So that's called background subtraction. So the key effect of that is we can isolate someone moving in their house, different from a podium or a chair or a desk, anything like that. So then from there, once we've gotten those key points in the image, we feed that, there you go, you see the old and the new and the end location, but we feed that into this algorithm called Huff line. That's named after someone, I think Thomas Huff. But essentially, first we highlight these key points like I just showed you. And then you have to, from there, understand that each point has a set of lines going through it. If you imagine any point on a plane has technically an infinite number of lines, but you can represent that right over here on this theta p plane as a sinusoid. It just, via calculus, comes out like a sinusoid on this plane. So this whole curve here represents just all of the lines through one point in the image. And if you graph a series of these, so here you can see where each line ends up. So the lines in the original plane turn into a point on the other plane. So if you put a series of these for all the key points in the image into a graph, you can see you'll get a bunch of sinusoids that are all unique, but they intersect at a couple key locations right here. So if you find these key intersection points, those are common lines in the image. So if, say, it's this red line here, say this red point right here, there's a lot of intersections. That means there was a bunch of points along that line in the image. So you can, if one line gets enough votes from each of these sinusoids, you can say that that line is present in the image. So why does this matter? Say we start with someone in their own home. If we want our program to be working properly, we'd want to be able to detect that this person is standing upright in their home. So first of all, we detect the points, the edge points like I was showing you, and I've highlighted some key ones, this red, green, and blue points here. We get their sinusoids and notice these intersections here, where the green and red sinusoids intersect. That's a line, that represents a line between the green and red points. And the same for the others. So if we graph that, there you go, you can see each of these lines. And then finally, if we grab this longest line, this is where it kind of becomes clear. The longest line that we see in the image, assuming we're just looking at the moving human body, we should detect essentially a line from a little higher than this, roughly from their head to about their feet or maybe the bottom of their torso. Long story short, if you look at the just body shape of a person, there's essentially the longest line in the image should be this vertical line going down your body. Now, when you fall over, that won't exactly be the case. You'll see that this line will rotate and be maybe more horizontal, things like that. So right now you can see if we get the theta, the angle of this line, it's about 90 degrees. That represents someone standing upright. So if we can teach the computer to identify this line and detect its angle, we can use that as an indicator of a fall. So here you get to see the funny part. To test our process in our program, I made a series of falling and non-falling test videos. They're highly professional, as you can tell, but this was more of a proof of concept, so not the most rigorous testing data set. But even with this alone, we can test for each individual clip. If the computer detects me as falling, then it just outputs a fall, and we consider that its decision on the video. So if we take the accuracy of these decisions by just dividing it by the total number of videos, we can get our results. So we got about a 76% accuracy at roughly 23 frames per second. So the accuracy is not bad. We'd like to improve it more, but again, this is a proof of concept. But the key thing is that efficiency as well. The 23 frames per second is pretty fast for one of these models to be running, especially, well, here, I'll get to some more improvements we could even do later. So first of all, the end goal of this all was, sorry, I don't know if I can move this out of the way. Let's see. Nice, there we go. Sorry, I don't know if people in Zoom can tell there's a little thing in the way, but so there is, our main goal here was to compare to existing neural networks. So sadly, the main ones on the market, these neural networks of like vision sensors you'd put up in your home, are proprietary because they're being sold for profit. So people don't want to put their benchmarks or their code out there because it puts them at a competitive disadvantage. So instead, what we're doing is we're going to post our source code and results out there so that anyone on their own time and their own privacy of their company, they can compare to our data, and hopefully it'll influence their policymaking decisions. Should we use a non-neural approach for efficiency, things like that. But we can also make these general comparisons. For one thing, we know that neural networks can have a very high maximum accuracy. They can be very successful with a lot of training and development. However, we found that even with this proof of concept, our non-neural Huffline system was relatively accurate by itself. And then not to mention, these are the main benefits, the efficiency. We can see rather than having a densely connected neural network, we just find one line and then we track its angle. So it's highly efficient and it's very easy to improve. Like I was mentioning earlier, traditionally coded programs like this are just much more flexible because you know what each line does. And you don't have to retrain a new model every single time you want to make a change. And then finally, the clarity. Again, there's no black box. I can outline like we did here in the slideshow, each and every step of the program. So how it gets from point A to point B, gets an edited video, finds the line, etc. And then finally, oh, hold on, it's a little bit frozen. There we are. Finally, just for some future improvements, I was happy with the accuracy, but I would definitely like to improve it. So this is where we focus on something that I think I brushed over actually on the results slide. There are some key weaknesses of our program that it struggles with occlusion, which just means obstacles in your way. So if there's a camera right there, half of my body is occluded by this podium. So obviously that can make it hard. Your data is restricted. And then also with multiple subjects in view. But these weaknesses being so well defined is actually pretty beneficial because if we want to improve our accuracy, we just have to develop our code and add some more pieces in to address these specific issues, but we can be confident that we can address one issue without influencing the rest of the model. And then a second thing we'd like to do for efficiency is we'd like to switch. This was coded in Python, which made it very nice and easy to code because Python's a nice language, but it's also highly inefficient. C++ would be a much faster language that I believe we could translate it over to there. We would see a lot of efficiency gain in the frame rate and things. And then finally, we wanted to use a separate indicator, maybe as a replacement for the Hufflines, or maybe to work in tandem with it. But we want to use the height width ratio of a person. So I got one more funny image to represent that. So these are two images of me. You can see when I'm standing up, this vertical line, like the tallest line you could draw from my head to my toes, is very long. So the ratio of that to this shorter width line it's a very high ratio. But whenever I fall, this ratio changes drastically. I essentially get wider and shorter, shorter, if that makes any sense. So if you see, if the computer sees a large change in that ratio, it could be an indicator of a fall. Maybe this could work in tandem to improve accuracy, or maybe it could even work by itself and make the system much more efficient. Sadly, we just ran out of time in the program to really develop this entirely separate solution, but I'd love to work with that more in the future. But other than that, I would just like to say thank you to, they're not here right now, but to my mentors. Oh, he's here. Hi, Dr. Lee. Thank you. So thank you so much for all of your help this summer. You're absolute huge help. We had these bi-weekly meetings that were invaluable in my progress on this program. And thank you as well to Dr. Boone for just your guidance, especially with the abstract and things like that. And of course, most importantly, the food. Thank you, Panera every morning, or most mornings, but and then just thank you to the Hillman Cancer Center for putting on such a great program. So thank you so much. Yes, any questions? Yeah.
Your accuracy, is that instant for each frame?
No, so actually, Dr. Boone was talking to me about this, because I clarified a little bit, because yeah, if we try to do it frame by frame, when does it detect a fall, when does it not? The problem is you can very easily manipulate that by adding in a lot of padded frames of no fall, things like that. So you can get a much higher accuracy than maybe your model represents. So what we instead really wanted to test at the end of the day was, can this model detect when there is a fall and not detect a fall when there isn't one? So we decided to run accuracy based on the entire video clip. If it ever thinks there's a fall, then we would say that it detected for the whole clip a fall, essentially. So this puts a little more stake on false negatives, I suppose. So it just makes it more clear. Yeah.
Does that accuracy account for like repeat tests, like for example, like sitting down or like bending over instead of falling? Does that go into that?
Yeah, so for some of our non-fall videos, some of them were sitting down. One of them, I think I was spinning around in a spinning chair, but long story short, yes, we tried to cover as many situations as we could in the negative videos to make sure it wouldn't trigger on anything. Yeah.
So,
Sorry, my bad.
how long do you have, like, did you account for like how long somebody would have to be on the ground before your camera would detect that it's a fall? And like, say somebody's on the ground looking for something and they're down there for a while. And as far as like somebody falling and being down there for a while, like how long will it be before an alert would happen to go out for it to be considered a fall?
Yeah, that's a phenomenal question, first of all, because there are two things I want to show about that. Let me run back to these funny clips. Look at this one in the bottom right. So this was one of our negative videos, which it was me crouching down pretending I was picking something up.
Right.
And the advantage of that is, as you can see, if you try to imagine where that line would be drawn, it's still roughly vertical. It's shorter than usual, but it still maintains that vertical angle, which is key because the model doesn't exactly detect a fall unless there's an angle. But then also you made a very good point about the delay after. If it detects one line being horizontal, it shouldn't automatically detect fall. And yes, we implemented, I believe it's about a 5-second timer that it has to consistently be detecting a fall. And if it did for that length of time, then yes, we would then indicate it a fall.
So did you experiment like with a flat body, like looking for something? Like, cause like, all right, when you fall, you're like curled up. But like sometimes people fall and they're flat.
Yeah.
So did you account for that whenever you're like looking for things or something? Like, is this model out here in the world? Like, because people have what is it called?
Non-neural.
Non-neural things in our house? Is this like?
Right now, so sorry, unless you were done.
No.
Okay. Right now, the industry standard is to use these like deep learning complex neural networks. They're not what is it? They're not inaccurate. They're actually highly accurate. But what we wanted to see is, could we achieve reasonable accuracy with a non-neural solution? So it still has its weaknesses. For example, you can't see it here because like I said, we have 9 non-fall videos. But only 2 of them are shown here. But a couple of them, yes, I did. And for the fall videos, I did fall on my side or things like that.
Yeah.
And it achieved reasonable accuracy, but like you can see, not 100%. So I would have to check specifically which ones failed and why. But yeah, essentially. Yeah.
So maybe I missed it, but who does it notify? Does it call like 911?
So right now it doesn't notify anyone because we're just trying to create the detection system. All that can be added on later of like, oh, what would you like to do if it detects a fall? But obviously we didn't want to call 911 every time I, fake fall on. Exactly.
My second question was, so is it going to be built to fit like per person, or would it be like, say if it's in a work environment? Would it detect everybody's height and width and things like that, like everybody that walks in a room? Or is it for like a person?
So that's one of the key weaknesses right now, is that it does struggle with multiple subjects. So we're workshopping different ideas of how we could make it be accurate and not get confused by multiple people walking in frame.
Okay. And is it, I'm sorry. I was just wondering if it's like, is it multiple cameras or is it just one single camera? Like say, like if you had it in this room right now, would it be multiple cameras on different parts of the room, or is it just like one camera in the back of the room that like maybe rotates or something?
No, that's another really good question because we had discussed that as well, because an issue is if you're thinking about drawing this line vertically, let me go back to here. In this example, imagine this stick figure person falls forward a bit, right? If they fall towards the camera, the line will actually still kind of be vertical, which will create an issue because obviously it'll think they have not fallen when they have. So our solution to this is we would have 2 or more cameras running at perpendicular angles so that no matter where you fall, if you're falling straight towards one camera, you're falling sideways from the other one's view.
Right.
So no matter what, at least one of the cameras can detect that fall. Yeah, Preetam?
You always manage to get quick questions,
I always do.
in terms of accuracy, that's like a really flawed metric. You know, like if it's really prone to producing false positives, which in this case will actually be okay because we're okay with notifying someone after you say so, or does it like have a lot of false negatives where it can't really tell if you fell at all?
So I didn't put it up here, I probably should have, but in the abstract I wrote earlier, we had a confusion matrix, which represents that. I believe it was roughly 22 to 25 for both false positive and false negative. So, or sorry, not for both, for like each of them. So roughly 11%, I think, would be false negative. So again, I mean, there are some parameters we can tune to the Huffline's algorithm. We used a library called OpenCV to simulate it. And its parameters, I can tweak how like the minimum line length for a line to be detected. So maybe it sees a line that's 2 pixels long. It doesn't really care, right? I think that's fake. But I can tweak that line length and the maximum line gap, which is essentially, you might see, let me go to one of these photos, sorry. Here, you might see there are these little black splotches in the image. So we had to make sure it could it could ignore small gaps, things like that. But I could tweak these parameters to increase either false negative or false positive, just depending on which one, like you said, which one we think is more important, you know? So, just sorry, does that answer your question? Okay. Anyone else?
But before we close,
Yes.
because, yeah, the introduction after the presentation.
Hello, I'm sorry, not being in this place, the people in the beginning of his presentation. I'm Ini Lee at the University of Pittsburgh Electrical and Computer Engineering. So the Adam Ferris from the Fox Chapel area high school, worked with us in the last 8 weeks, and then you can see his passion on taking his passion the picture on the ground. So we started to looking at a solution to identify the adult have some fall accident in the house, and then without taking very high resolution picture, because to have some privacy, to protect the privacy issue. So when you see his picture here, but that's not going to be the actual picture, but we wanted to starting from this a very coarse resolution picture. So, but what we have right now is a webcam, so you can identify his identity. But originally, in the future, we will have a hardware. We'll just create this coarse resolution. So that's our the goal of our project. Yeah, thank you very much for your attention to his presentation. Thank you so much, Adam Ferris. Thank you.
Thank you, and sorry we were running a little ahead of schedule. This always happens because you can tell they're not faculty yet because they're always on time, right? We're never behind schedule. We're always ahead of schedule in these events. So let's give one more round of applause to all of the students who did the presentation. Really nice job. We're going to take a break now until 11:15. So we'll come back here at 11:15. I think there might be a little bit of coffee and pastries left. Go get it. Even though we're going to have lunch in an hour afterwards, that's okay. Keep eating, keep drinking. Again, for those of you who just came in, restrooms are on this side of the wall. You can go out the door and around. So again, congratulations to all the students. Back at 11:15 for the final round of talks. Great job.
Okay, I'm Allison.
Are you the one from Olivier?
Yeah, I'm a sponsor. Yeah.
Yeah.
Yeah, this is my last year. Probably like yes, yeah, I'm doing it. Yeah, probably like a billion. And you were in the bio. Okay. Yeah. Okay, I think,
We have 1 minute for next year. Cross training. And then we had one or a few minutes from the
okay, that's some students are not in. That's great.
Yeah, that's like the advantage of competition. Right? This wasn't the case before 2015. We're still like figuring out how to adjust to yeah. Very rare. I'll figure out how the students learn how to manage.
Yeah, it's like my eyes.
This is the 15th year of the program.
I feel like you said what it spends. How long am I?
I've been all these somewhere. I don't remember. As the years go on, it's harder and harder, but it's been a while. It's fun. Well, 2/3. It's related, it's 5 minutes. Everything 5 minutes. I should
Does she know?
Yeah.
So how was the work?
That's what I wrote on the first page. I knew that these stuff, you get something else. You could have said that other things. You can't do. Yeah.
And did you plan a series like this? Like that's actually like the initial.
Oh, yeah. Running like. It's hard to know. That's not, I mean, you get part of this for 6 or 7 years. Either way, I would rather learn it, don't like it now. I just want to do, and then we'll be here in about an hour. Hour and a half. Yeah. I get it. Yeah. It's based off of mentors of the year. And then I try to put, if I can, put the people on first. I think the hardest one. Just because I've already done it. In theory, might be less stressed out there. In theory, yeah. But otherwise, it's just based on the mentor. Or like. Way over has time to do that. Yeah. Yeah. So nice. On the street, you just on. He's up to like 6 a.m. So he's probably been up for 40 hours straight.
Hello, everybody.
I think it's all right. There are fewer now than ever, right?
No, that's just like this.
Well, so like I said, NCI is hard. So it's saying either one. I don't know. Yeah. It is long. What's the difference? Like, sorry. She was so excited for a lot. Because originally, there was one student, Jonathan, from last year. He was from last year, he was supposed to get this year. It ended up, like, all weekend in the program saying he was doing another program. He was trying to vote remotely and do this working. So he was supposed to be here. And then there was yeah, right. Yeah. You know. I don't even know where they are. I just walk all the way across. I had no idea. Because our cardiac facility, you can actually do it through buildings, do the same thing. You can go in certain buildings, go up elevators, take a tunnel, take another. Yeah. And the weird thing is, there are different ways of getting what you gonna do is you can watch all drinks. Yeah. Probably, I don't know. There's food back there. Did you all? You guys know?
At the end,
I see what they use
Right at the end. Yeah. We're getting better.
Yeah, we did.
I feel like we did. Nice, great. Last few. I've met you in my And that's where, you know, again, it goes. Oh, there's. No.
I think so.
We're about to get started.
All right. We're going to get started on our third and last session here. So we have 5 more great speakers who are going to tell us about their work this summer. And for those of you who are, again, just coming in, this is repetitive for everyone who's been here. I want to say thank you for being here. Thank you to the mentors for working with these students and giving them direction and leadership and someone to talk to and listen to and volunteering your time. Really, really appreciate it. You guys are the program. I'm just here talking in front of everyone. So it's my pleasure to start the third and final session. So the first one is Mikaela Buscher.
Hi, everyone. So it's such a pleasure to announce that I was happy to work with Mikaela. And since the first day she started it, she was very enthusiastic. And whatever the research questions that I throw at to her, she would always come back with the answers. And what can I say? Girlie, is your stage.
Okay. Hi, my name is Mikaela Dassanaike-Perera. I'm going to be a rising sophomore at North Allegheny. And along with my mentors, Murat, Busha, and Richard, my project this summer was the usage of EEG-based BCI system for emotion regulation and autism spectrum disorder. Okay, so autism spectrum disorder, or ASD, is a neurodevelopment disorder often accompanied by impaired emotion regulation, where individuals with ASD have more trouble managing their negative emotions. So this leads to maladaptive behavior such as tantrums, temper outbursts, aggression, and self-injurious behaviors. And so the Emotional Awareness and Skills Enhancement Program, or EASE, a 16-week behavioral intervention technique, was developed to help them manage their negative emotions. And so in combination with the EASE treatment, we developed an EEG BCI system to investigate the significance of ease treatment by using pre and post visit or before and after the ease treatment via machine learning. So a total of 39 participants, where the average age was 15, was asked to play an affective Posner task card game where subjects were shown 2 cards, the white squares, and asked to pick a card with a star on its back. Participants were given feedback, win, lose, or too slow, based on their response times. We focused on game 3, which included deception. So 60% of correct responses or wins were given regardless of how fast the task was actually performed in order to induce an emotional reaction. During the game, EEG data was collected for each of the 17 ease participants and each of the 22 non-ease or control participants. A total of 94 spectral and temporal features were calculated at 7 different brain regions to differentiate pre and post visit data for each ease and control group separately. The spectral features were calculated using the Welch paradogram method, which reduces the variance of the paradogram by averaging. And the temporal features were calculated by averaging them over a certain time window. So these are a couple of examples of the features that we extracted. So on the left are the spectral and on the right are temporal. So the image on the left is an example of random forest classification, where the computer is trained to identify a certain result based on the data set. So in this experiment, 3 random forest classifiers were developed to ascertain whether there is a difference between pre and post visit for both the control and ease groups using the EEG features extracted during game 3. Dr. It's got. So there's difference between pre and post visit for both the control and ease groups using the EEG features extracted during game 3. So the data was split into 2 separate data sets for training and testing, with a split of 80-20 to test the classifiers on unseen data. 5-fold cross-validation was performed on the training set to search for the optimal number of trees across all folds, and then used to classify the test set and compare the ground truth. 3 performance matrices, accuracy, sensitivity, and specificity, are all reported to highlight the performance of the model.
We have to go back on power.
Yeah. So the classification results of pre and post visit for the control group indicate 78.65%, 76.52%, and 80.74% for accuracy, sensitivity, and specificity during the win condition. While the results of the classification of pre and post visit in the ease group show 88.24%, 85.19%, and 91.26% for accuracy, sensitivity, and specificity, all respectively during the win condition. So consequently, the results of the random forest classifier in the ease group outperformed the classifier in the control group for lose and slow conditions. So it can be seen from both tables that the classification of pre and post visit for the ease group outperforms the control group in accuracy, sensitivity, and specificity. So this may stipulate that there is a greater difference between the neural responses for pre-ease and post-ease treatment. Additional experiments need to be investigated to find the most informative EEG features associated with emotional regulations, which in turn will allow us to use these features as biomarkers for non-stress and distress conditions. Feature selection strategies can be applied, such as sequential forward selection algorithm. These are all the references that I used. And then for my acknowledgements, I want to thank my mentors, Dr. Murat, Busha, and Richard, as well as Dr. David Boone, Stephen Jones, the University of Pittsburgh, the Department of Biomedical Informatics, and the UPMC Hillman Cancer Center for providing me with this opportunity. Thank you.
Questions?
So for that card game you're talking about, would that be testing procedure, like?
Yeah.
Essentially, you're like testing the EEG system or?
So we're using the EEG system as so that's where we gathered our data using that that game. So the way that we set it up is we had kind of like a helmet using like the EEG nodes on each volunteer. And so we just used that card game in order to get the emotional reaction and just measure our data. And that's how we got it back.
Since you guys were able to really accurately use the random tree model, does that mean that there's a difference between the pre and post conditions using EEGs?
Yeah.
There you go.
Thank you.
All right. I think Om's next, right? You should be able to share and or would you like to introduce? Yeah. Perfect.
Hi everyone, I'm Yijun, a research associate in Dr. Zhang's AI lab. And I will introduce a sophomore student in University of Michigan, majoring in computer science. During this summer, has worked with us and contributed to two main projects. The first one is that based on the experiments we have done, he have contributed to write the manuscript. And the second part is that based on the web application we have got, and he participated to generate a user manual to make it more convenient for users. Okay, let's welcome
Thank you. Can you hear me all right? Am I good? Can you hear me?
We can hear you. Let me try to make it louder. I don't know how to do that. Go ahead.
Hi, my name's Om, and it's just a quick overview of what I worked on over the course of the summer. So my work was twofold. The first part involved participating in a manuscript development with my mentors for the optimization of hyperparameter tuning in predicting late onset breast cancer metastasis. This was facilitated through the use of a package called Single Hyperparameter Grid Search, and it can help us to further explore clinical applications for deep learning. For some background, deep learning is a subset of machine learning which focuses on training neural networks to perform tasks without any prior explicit programming. The image at the bottom highlights the main difference between these two methods in that machine learning requires human intervention beforehand for feature extraction, while deep learning integrates this into its learning process. Deep learning also aims to mimic the human brain's structure and function to recognize patterns and make decisions. Neural network consists of interconnected layers of artificial neurons called nodes, and each of these layers processes the input data and passes it on to the next layer, allowing for hierarchical feature extraction. Hyperparameters are essential to the performance of deep learning models, but what exactly are they? They're configuration settings that control behavior of deep learning models during their training. As can be seen from the image to the left, different values of hyperparameters result in varying model performance scores. And this is where hyperparameter tuning comes into play. It results in better hyperparameters that, when used with model training, they result in better model parameters. The right combination of hyperparameters and consequently their model parameters, it can significantly impact model accuracy and its generalization capabilities. Two of the most common types of hyperparameter tuning techniques are grid search and random search. Grid search systematically evaluates all of the possible combinations to find an optimal set, while random search just keeps searching randomly and then picks the best one at the end. They each have their own pros and cons, but they have a common limitation, that they're both extremely computationally expensive, especially when the number of dimensions increases. So this is where SHGS comes into play. It attempts to solve the large solution space problem by assisting in the search for reduced range of hyperparameter values that seem to be performing better than the rest of the range. It's beneficial because it helps us with the pre-selection process for any subsequent grid searches. And these would be looking within a more constrained range, allowing for faster completion times and better model performance. And the flowchart on the right here, it highlights the process that SHGS goes through when it's run. So it starts with the 3 inputs at the top from the user, and then it iterates through all of these until all of the iterations have completed. Each iteration starts with a selection of background hyperparameters, which are hyperparameters that are different than the target hyperparameter. And then the model is tested at each value of the target hyperparameter range, with each background setting being the same, to see how only the target hyperparameter affects the model performance. In regards to the deep learning manuscript, we used extensive literature search to gain a knowledge base and identify evidence that can be used in our research. Includes ideas that corroborated our results and also ones that suggested against it. References were managed through a software called Mendoza, which allowed us to keep track of, include, and share our references within the manuscript. The flowchart that was made for the visual understanding of SSGS was through a software called Lucidchart. And lastly, we used Python packages such as matplotlib to plot the figures that were used for the manuscript, as can be seen from the image on the right. Second part of my work involved medical web application user manual for IMED, which is a platform developed by my PI's lab for data mining, machine learning, prediction, and clinical decision support, all with a focus on breast cancer. This would ideally enhance the medical research and clinical practices through insights given through the IMED app. Objective of this manual was to create a user-friendly guide to help facilitate and effectively utilize IMED and its functionalities. Methods for the IMED web application started with a comprehensive test of the existing infrastructure to learn how it all worked together. I also used bookmark system, custom style heading formatting to let other programs opening the manual understand how it's structured. With the help of my mentors, the user manual was added with Flask, which is a micro web framework written in Python, and it's the backend for the entire IMED application. It's also deployed and hosted on Amazon Web Services, which allows multitude of cloud computing platforms. Overall, manuscript still a work in progress, but I was able to complete a draft for the sections I was assigned. Key focus was the investigation of hyperparameter meta-tuning, where I specifically focused on learning rate, momentum, and decay of the 8 total hyperparameters that were discussed. Mainly, we focused on relationship between hyperparameters and their impact on model performance and how certain hyperparameters have more of an influence on performance than others do. For the user manual, objective was a comprehensive guide for both professionals and patients regarding the IMED web app, and we were able to successfully incorporate my version onto the website. Future directions include exploring new domains and applications where deep learning techniques can be applied, including growth and potential applications for deep learning clinically. There can also be improvements that build upon SSGS to further refine and automate hyperparameter tuning in deep learning. To share knowledge with others, we can present our research findings and publish the results for others to read. Lastly, for IMED, we can start to develop a larger user base to gather feedback that helps in the continuous improvement of the web app and its manual. Here, I'd like to take a moment to acknowledge my mentors, Drs. Jia Jiang and Yujin Zhu, for all their help and collaboration throughout the summer. I'd also like to thank Dr. David Boone, Stephen Jones, University of Pittsburgh, Hillman Academy, and the DBMI for everything throughout this internship. Thank you for your time.
Any questions? So can you, because you, I think you're getting some echo. You're the only one who's worked on a manuscript that this summer. Can you hear me okay?
It's kind of hard.
It's okay. We can talk later then. Well, if you're having a hard time hearing, that's okay. We'll just say congratulations.
Sorry, there was a lot of echo. I couldn't hear anything.
Yeah, it was echoing on this end too. All right. Sure. Not up super loud. All right. Next up is Divye, who is online as well. Go ahead, Ho-Ting, introduce him.
Hi, good morning, everyone. I am Hao Teng. So let me first introduce our student, Divye Arora-Jain. Okay, so Divye is a high school student from Montreal High School, Pennsylvania. He conducted his summer project in our research lab in electrical and computer engineering department at the University of Pittsburgh, mentored by Dr. Liang Zhang and Dr. Hao Teng. His research project is about utilizing hierarchical graph learning model to predict human behavior based on MRI-derived brain connectivity networks. Okay, so Divye, you may start your presentation now.
All right, can you guys hear me okay?
Yes.
All right, so hello, my name is Divye Arora-Jain and I attend Montreal High School. My project this summer was to work on deep learning for adult self-report score prediction via brain networks. My mentors for this summer were Dr. Zhan and Dr. Tang. So a little bit of background around understanding human behaviors through brain networks. Put simply, a brain network represents the relationships between brain regions. Each brain network has nodes and edges. Each node represents a region of interest, or ROI, while an edge represents the relationship between the two nodes. However, to actually predict human behaviors, we need a deep learning model. A deep learning model is an AI algorithm that allows a computer to learn as any human does. For this specific project, a hierarchical graph learning framework was used. The difference between this and a normal deep learning model is that this organizes nodes into communities based on their similarities or differences. In order to measure the human behaviors, we need to have some kind of scale. We chose the adult self-report score as it is a good way to assess human behaviors and is easy to understand. Assess human behaviors just means to understand how a person reacts to a situation. So if they're an introvert or an extrovert. Also for this study, the mean absolute error or MAE was measured. More about the MAE in future slides. So a little bit more information about deep learning. As stated in the previous slide, deep learning is an artificial intelligence algorithm that allows the computer to learn and make predictions like a human. As shown by the picture in the top right, deep learning is a subset of both AI and machine learning. A deep learning model is able to train itself to perform tasks such as speech and image recognition while requiring fewer human interactions. This is allowed mostly because of a multi-layered neural network that can process complex data and then extract meaningful patterns. The image on the bottom left shows this. A deep neural network contains many hidden layers that are able to extract information that many other non-deep neural networks cannot. For example, the picture on the bottom right shows that while machine learning requires a human to interact with the computer and complete the feature extraction, a deep learning model can do this on its own. Additionally, a deep learning model can be trained to achieve higher accuracy on certain tasks compared to machine learning. So, what's the goal of this project? The goal was to utilize fMRI-derived brain networks and a hierarchical graph learning framework to improve predictions of human behaviors based on the network community structure and features. So the data set for this project came from the Human Connectome Project, or HCP. It contained 1,000 subjects, of which 456 were men and 544 were women. The average age of these subjects was 29 years old. We will go over the training and validation in the next slide. The brain networks used in this data set were fMRI-derived brain networks and represented in the form of adjacency matrices. This is because it is much easier to input numbers into a deep learning model than it is to input a picture. The matrix is just an easier way to represent the brain network and input it into the deep learning model. Finally, the dataset includes a ground truth value for each ASR score for every subject. The ground truth value is just what the actual value is meant to be. This ground truth was found from a 126 question item questionnaire that is used to find an adult's ASR score. So, dataset continued. In this project, a total of 4 ASR scores were measured. The first is the withdrawn score. This reflects the tendency of a person to be reserved or avoid social interaction. The second is the attention score, which measures the level of focus or concentration a person has. It also measures how easily one can be distracted. The third is the intrusive score, which assesses disruptive actions and the inability to control impulses. The fourth and final one is the externalizing score. This measures outward expressions of negative behaviors or emotions. In other words, if a person conveys their emotions to one another. A high score in any of these areas suggests greater challenges in social interactions, focus, impulsivity, and external expression of negative behaviors and emotions. So after receiving the data and having the deep learning model set up, we need to train the model to accurately predict human behaviors. We do this by creating a training set and a validation set. In this case, 800 subjects were used for the training set and 200 were used in the validation set. To first train the model, we have to specify a number of epochs. An epoch is the amount of times the model goes through the entire training set and updates its weights and specifications. The number of epochs chosen depends on how the model reacts to previously inputted epochs. The mean square loss, or MSE, is then used to minimize the difference between the prediction and ground truth. We also have to validate the model to see how its accuracy is progressing. In our case, the model was told to give a validation loss every 10 epochs. The lower the validation loss, the closer the model's prediction is to the actual value. So once we have the validation loss, the MAE, or a mean absolute error, has to be calculated. The MAE is found by square rooting the validation loss and measures the difference between the predicted values and the ground truth value. If you look at the diagram below, you see that a validation loss of 25 would give you a mean absolute error of 5. This means that the predicted value that the deep learning model outputs will be anywhere in the range of the actual value -5 or the actual value +5. So the total results. The picture to the right shows a bar graph containing all the MAE values for each ASR score. The x-axis describes what ASR score is being mentioned, and the y-axis describes what the corresponding MAE score is. On the left are the MAE scores that were found with our model. However, these scores do not beat current baselines. The current baseline ranges anywhere from 0.7 to 2, depending on what ASR score is being tested. While these scores don't beat current baselines, it is worth mentioning that with additional time and tuning, this model shows great promise. So a quick summary. A hierarchical graph learning framework can effectively predict human behaviors. Also, deep learning and brain networks can help us better understand human behaviors. Additionally, this graph learning framework can give clinicians insight on patients' mental health and help verify an ASR score that was received using a normal questionnaire. In the future, the deep learning model can be optimized to help generate better results and increase performance. Additionally, future work can be done to expand on the research to help explore brain network applications in various other clinical phenotypes. Overall, this deep learning model has great potential to accurately predict human behaviors if thoroughly researched and executed. So I would like to acknowledge thank Dr. Liang Zhang and Dr. Ho-Teng Tang for their unwavering commitment to me this summer. I would also like to thank Dr. David Boone and Stephen Jones for setting up this academy and guiding me through any problems that occurred along the way. Lastly, I would like to thank any funding that my mentors used to help support my research. Thank you.
Any questions? Good, Bill.
So this was used with questionnaire data. Do you think that your model could be applied to different types of questionnaire data? Or is it specific to this, is it ASR questionnaire?
So if you could get like a different questionnaire and get the results of that, and then train the model to relate the brain networks to the results of that questionnaire, I think you could probably set it up in a way that it could accurately predict the results of that questionnaire instead of the ASR.
So any other questions? All right, great work. Dr. Murray, you want to come introduce?
Good morning, everybody. I'm Sandra Murray. I'm a professor in the School of Medicine, Department of Cell Biology, and it is my pleasure. And also the president, coming in December, I will be the president of the American Society of Cell Biology. That's big to me, so I needed to say that. Continuing on, I'd like to say it has been a pleasure to have Malynn Jones working in my lab this summer. For you who need to get letters of recommendation and those who write letters of recommendation, one of the things you once said in there is that terms like, and what I look for is bright, team player, capable of working independently. And then the next sentence should give you an example of that, so you know that the person isn't just saying that. So that in the letter, it should go on to say, here's example why X is bright, independent. And the teamwork you can kind of leave alone and not have as part of your example. But let me tell you why Malynn Jones is capable of working independently and bright. When the rest of the team went to the Howard Hughes Institute in order to collect data, Malynn stayed in Pittsburgh and taught herself how to use a very complicated imaging 3D, 4D program called the Mirrors by looking at movies or videos from numerous videos from that were on their website, as well as going on YouTube and going to the University of Pittsburgh Imaging Center for assistance. That was only for 2 weeks. By the time we came back, Malynn could use the program and even tell me how to use the program. That's hard. At any rate, I'd like, without further ado, to introduce Malynn, who is a senior at the Pittsburgh Obama Academy. And it's a pleasure, Malynn. Thank you. I know she came in a lab coat because she means business.
Well, like my mentor said, hi, my name is Malynn Jones. I'm a senior at Pittsburgh Obama Academy, and today I'll be talking to you about gap junctions. So the three main points of my talk are gap junction plaque definition, the internalization and vesicle formation, and lastly, my third main point of my whole project is the fate of annular gap junction vesicles. Gap junctions are channels that allow cells to communicate with one another. Gap junction channels are made of proteins called connexins. Gap junction channels are formed by the pairing of half channels called hemichannels or connexons. Gap junction channels are aggregated into gap junction plaques. Gap junction plaques are removed from the surface by an internalization process that releases annular gap junctions. The removal of gap junctions is a method for reducing cell-to-cell communication and regulating cell behavior. The fate of annular gap junctions is poorly understood. The goal of my project was to analyze the fate of annular gap junctions. In this The first photo, you see me an example of a lattice light sheet microscope that my mentor used to analyze the data at the Janelia Research Institution. The next photo is the Janelia Research Institution located in Virginia, where my mentor and her team collected my data and actually saw my data. Then I got the data and analyzed the data through a software called Emirus, where I track the data, track the movements of the annular gap junction vesicles over time through 3D images collected by the lattice light sheet. In this video, you will see two cells, and you will see the two cells right here, and then you'll see small yellow particles that indicate the annular vesicles, and you'll also see a bigger particle that is the gap junction. Okay, that. This 3D rotation over time allowed us to track and analyze the annular gap junctions. That's the back of it, and then here's the front of it as well. In this, you see that I selected the region of interest to allow myself to analyze the annular gap junctions over time. The computer program was trained to select annular vesicles with a diameter of 0.5 micrometers or even bigger. The results for my project were that the average annular gap junction track speed was 0.7 micrometers per second plus or minus 0.3. The annular gap junction vesicles were observed to fuse with the membrane vesicle, divide and flatten out the cell membrane, and possibly recycle. The frequency of these events are still to be determined with the Emirus software. Annular gap junctions were tracked to determine their fate. They divided, changed shapes, associated with the membrane, and possibly recycled. This information will increase our understanding of gap junction protein turnover and the role of annular gap junctions in protein delivery to other organelles, including the plasma membrane. I would like to thank my mentor, Dr. Sandra Marie, because she was a very big help with me, even though she was gone for a long time at getting my data. I would also like to thank Dr. Selma Farah and Dr. Antonio Cooper, because they were also amazing help when Dr. Marie wasn't here. I would also like to thank Dr. David Boone and Stephen Jones for allowing me to have this great summer doing interesting work for this project. I would also like to thank Colin Wallace and Simon Watkins from the University of Pittsburgh Cell Biology Imaging Center. And I would also like to thank the University of Pittsburgh and the Hillman Academy. Any questions?
For the 3D and 4D imaging like that you showed, what software do you use?
It's the software, it was Emirus. You basically, they transferred the image from the lattice light sheet, and then they sent it to, they made it like they put it on like a document so I could be able to open it on the software, and then I could track it, and I could see the sizing of the cells and do everything else to see like how they work. Do the cells go anywhere else? Do they go back into the gap junction and everything else? You're welcome.
Were the images on the lattice microscope, were they immunofluorescence?
Yes, they were human adrenal tumor cells, emerald green and fluorescent connexin M cherry red.
Okay, that's not a simple task to get immunofluorescence working, so kudos to you.
Thank you. Well, thank you so much for listening, and I hope you guys gained a new knowledge like I did this summer working with this as well.
Hi, it's my great pleasure to introduce Shaun Fernando. Shaun is a student from Los Angeles High School. He has finished many AP courses in calculus, biology, and computer science. Shaun is also a competitive national tennis player.
Before this summer, Shaun had already participated in many research activities from his CV. I can see that last summer, he developed a machine learning approach to analyze and predict stress response level based on biological factors. This summer, Shaun works with my lab to apply transfer learning to enhance infectious disease case detection. Shaun possesses exceptionally programming skills, a keen ability to grasp new concepts quickly, and a natural talent for collaborating effectively within a team. Shaun.
Thank you for the introduction, Dr. Ye. Good afternoon, everyone. My name is Shaun Fernando, and my project is titled Applying Database Deep Transfer Learning to Enhance Infectious Disease Case Detection. So in the course of infectious disease outbreaks, the sharing of electronic medical record data, or EMR, is a necessity due to single healthcare networks not being able to use only their own data to build comprehensive case detection models. This sharing further allows quick and effective responses to be facilitated to deal with such outbreaks. However, different data distributions between settings cause model performance drop in a new setting, mainly due to differences in patient populations and clinical practices. Database Deep Transfer Learning, or DDTL, offers a promising solution to this, as it is able to take in similarities and differences between data in different settings into consideration. So transfer learning defines the ability to utilize a pre-trained model or data to a new task in a different, smaller data set, which subsequently saves the time and resources of training multiple models. For the context on the strain of model training, Google's language representation model, BERT, is trained on 16 cloud TPUs, totaling 64 TPU chips total for 4 days. This is equivalent to 60 desktops running for 4 days nonstop. Additionally, transfer learning is utilized in image classification primarily, and its use for clinical non-image data has not been studied thoroughly. Deep transfer learning, a subset of transfer learning, utilizes networks as models, which by themselves need even more massive amounts of data to solve a task efficiently. Combining these two ideas describes DDTL, which will be used and assessed in this project. So transfer learning is the broad idea of transferring models or data. Deep transfer learning applies this idea, and database deep transfer learning is one use or instance of deep transfer learning, transferring data between settings to create a deep network for the new target setting. So with all this in mind, the objective of this project is to utilize database deep transfer learning to assess the transferability of healthcare system source data to a new setting, thus creating and assessing a target setting infectious disease case detector. So data was collected from 2 healthcare settings, Intermountain Health, or IH, and UPMC, where Intermountain Health acted as the source setting and UPMC acted as the target setting. This data was extracted from clinical reports using Topaz, where the presence or absence of 67 infectious disease symptoms in the form of UMLS concepts were identified. This further allowed the presence or absence of influenza or RSV to be identified as well. This data was collected over 5 seasons from 2010 to 2014 for each disease. This diagram illustrates one instance of data collection for a patient X during season Y. This patient's clinical reports were fed into the Topaz natural language processing tool, where the presence or absence of these 67 infectious disease symptoms were extracted. And based on these presence or absence of these symptoms, the presence or absence of flu or RSV was extracted as well. The data collection process was identical for both settings, Intermountain Health and UPMC. So in order to utilize the DDTL method, a domain adversarial neural network, or DANN, was implemented to create a target setting case detection model using both source and target setting data. The DANN consisted of a feature extractor, which created features that can be utilized in the rest of the model, a domain classifier, which allowed the settings of features to be predicted, and a label predictor, which used the extracted features to predict class labels, which in our case is the presence or absence of flu or RSV. The loss was computed at the ends of the label predictor and domain classifier, and backpropagation was implemented to train and tune parameters of the model. The lesser the error, the stronger the model can distinguish between settings, meaning a better classification model was achieved. So in order to assess the performance of the DANN, 3 baseline models were created. First was a source model, which used source setting data to train and test the model. Second was a target model, which used just target setting data to train and test the model. And finally was a combined model, which used both source and target setting data to train and test the model. These models acted as traditional neural networks to compare against the DANN. The data used for the DANN was the same as the combined model, but the structure of the DANN was significantly different, as mentioned in the previous slide. So in order to quantify performance, the AUC value was calculated for each model. AUC, or area under the ROC curve, compares the amount of correctly identified positive cases or total positive rate against the amount of correctly identified negative cases or total negative rate. The blue bars shown in these graphs represent the DANN model performance, and the orange, green, and red bars respectively represent the source, target, and combined models performances. Based on the results, we can see that during some seasons, the DANN showed improved performance over the baseline model, but the baseline models also outperformed the DANN as well. The performance for the DANN for influenza detection also seems to have an increasing trend as years go on, which is something that could be analyzed in further research. The highest AUC value by the DANN was during the 2014 season for influenza detection and for the 2010 season for RSV detection. So the inconsistent AUC values in the models shown in the previous slide can be attributed to a lack of data present in the target setting training environments. So during some years, there were almost lower than 5 positive influenza and RSV cases, making training a target baseline model, combined baseline model, and DANN model increasingly difficult. The presence of more positive influenza and RSV cases in the source setting training data could have also caused overfitting to the source setting, lowering target setting prediction performance. So in conclusion, this project confirms that the DANN was able to transfer data between settings while sustaining some model performance during seasons, but has room for improvement due to inconsistent AUC values. In many cases, the baseline models outperformed the DANN, which could have been due to overfitting to the source setting and not accounting for variation between settings. So throughout this project, limitations and potential extensions were identified. A key limitation was that hyperparameters were manually tuned, which might have lessened AUC values and lowered the overall performance of the model. So in order to find the right hyperparameter combinations, a grid search or random search could have been implemented as shown in the extensions diagram below. These searches set ranges for 2 hyperparameter values and find a combination yielding the greatest model performance. The difference between these two is that in a grid search, the range has discrete intervals that form this kind of grid pattern, whereas in a random search, any values in the range can be used. Some extensions were that different approaches to transfer learning, such as model-based transfer learning, could have been utilized along with more infectious diseases to broaden the case detector. Furthermore, because the data set was so small, a smaller structure of the DANN with smaller nodes as well as less hidden layers could have been utilized as well that might have improved the accuracy of the model. Metrics such as accuracy, sensitivity, and specificity could have also been assessed to gain an improved view on what was causing a performance drop in the DANN. So I would like to thank my mentor, Dr. Ye, everybody who helped me with this project, including Yuho, Jason, and John, as well as Dr. Boone and Stephen for facilitating this program, as well as all the other grants that made this project and Academy possible. Thank you.
Any questions? So basically, you built a model to try to find diseases and then track how they spread throughout the years?
Yeah, so that is kind of an extension of it. What was done in this project was that based on clinical reports of patients, we could detect the presence of infectious diseases and then how they can spread throughout a setting. Yeah. Yeah.
So like, is it limited to like a state, or is it broader?
Yeah, so this data was just used for UPMC here in Pittsburgh, as well as Salt Lake City for the Intermountain Health. But this could have been brought into any healthcare system around the nation, which could increase infectious disease case detection throughout the whole nation, which would be really helpful.
And it'll be able to, like, so say if somebody had, I don't know, let's say patient X had the flu, or
Yeah.
not, like something like more serious, right? And then they travel, but they went to the hospital. Will you be, your model is basically saying that you'll be able to track it and the people that got it, and then be able to see how it'll be able to spread throughout like say, in a certain amount of time, let's say 12 months, it'll spread to a certain like bigness, you get what I'm trying to
Yeah,
say?
it's not much of like a tracker. It's more detecting based on symptoms of an existing patient.
Okay.
Based on like the presence of a disease just being exhibited in the patient. So
Okay.
Is the UPMC data UPMC wide, or is it a specific hospital?
I think it's UPMC wide. Yeah.
I'm just so surprised there's so few.
Yeah.
Have you looked at, what year does the data go up to?
It goes up to 2014 for these data.
I'm wondering if you have access or could get access to newer data.
Yes, yeah.
After the pandemic, then people were probably testing more frequently for influenza, whereas before you come with flu symptoms, there's very little treatment unless you come very early with Tamiflu or something.
Yeah, of course.
Would the data, maybe if you can get access to data where they could train your model better. I don't know if that's true or not, if there's an increased rate of testing over the last few years.
Yeah, that's a really good point. I just like intuitively, I think we should see that because a lot of people are being more conscious, of course, for COVID. So yeah, that would also help just train the model better and improve the performance. So.
Greg also now at the Shaun have also he had figure have access to the 10 years of patients.
Oh, for the last 10 years?
Yes.
So maybe there'll be better data in the new, sometimes getting that IRB access is a little difficult to navigate in our short window of time.
Yeah. And also it takes time to update the random thing, cleaning patients.
That's the biggest part of it.
So what, the transfer itself or the? No, that's what compare with this data for the experiment, it takes but John already know how to run the program. Yeah.
Excellent. Any other questions? Great job. All right, and can we give one more round of applause for all the students who presented today and the awesome job that they did? Super great work, really proud of all of you. A couple of things, I don't know if the food's here. It's supposed to be here. If not, it will be here soon. It will be set up right out here. Everyone's welcome to join. All the parents that left, please call them, tell them to come back and eat before they go. And then you can come and join us at the assembly at 2 p.m. The assembly building, which is only about 3 blocks down the street by the Cancer Center, for the graduation at 2 o'clock. And then the other thing I'd like to do before students start moving away is get a picture of all of you together. I don't think I have a group picture of all of the CoSBBI students together, the ones that are still here. So why don't we do that? Try to do that before we eat. Maybe we can go outside on the roof and take that picture. If the door is unlocked. And everyone at home, thank you so much for participating as well. We're going to sign off now, but really appreciate all that you did and great job, students.